Nanti boleh share ke saya ya?
Boleh. Sekejap tengok boleh tak dah. Okay. Assalamualaikum warahmatullahi wabarakatuh and a very good morning to Dr. Zulfan and all the students here. So basically, I would like to say thank you very much to Dr. Zulfan for taking your time today, actually early in the morning on public holiday, to share actually your expertise with us, especially on the use of Aspen Plus. So just to give like a short scenario, what happened is that in UITM, basically all the students are chemical engineering, and we actually use Aspen High Sys for teaching and learning purposes. However, in one of the project, a collaboration project, we intend to use actually Aspen Plus because we want to like model the membrane reactor actually using MATLAB, and we found out that if using Aspen High Sys, we cannot do it. So the only way to do it is by using Aspen Plus, and that is where we plan actually to learn more on the Aspen Plus. And today, we have the postgraduate and few undergraduate students that are doing the project on the modeling of, actually we are doing project related to the dimethyl ether production using fixed batch reactor or membrane reactor. So do you have any question on that, Doctor?
It's basically no, yeah. I mean, I received a quick list of questions from Aina,
Yeah,
right? From
I
Aina.
know.
So it's I mean the introduction of that question is very good. Yeah, she's like a MSc or PhD student.
Aina is basically a MSc student.
Yeah, I mean
So
the
so
email is very excellent. Yeah.
yeah, she's hoping to convert to PhD actually she just started her master uh last week actually, but she already done the project since August. So she completed her undergraduate study in July or August, so she
Okay.
did it. So
Okay.
she intend to actually convert a PhD.
Okay.
So she just registered as a master's student last week,
Okay.
but then she have started actually to do simulation.
Okay.
So I think she have a lot of questions, and we also have like few students that are undergraduate. So Aina is basically the postgrad. Others are undergraduate students. So they also would like to learn about this Aspen
Yeah.
Plus software.
Okay.
Okay. So
Yeah.
without further ado, okay. Perhaps we can start our workshop with Surah Fatihah. Then we can start our workshop. Okay. Okay, Dr. Zulfan. So the floor is yours, Doctor.
Okay.
Thank you.
Okay. Good. So I will just start sharing my screen. And this is a minute. Yeah. Um. So the so yeah, this is like public holiday, and then early in the morning. So I think we can make it as relaxed as possible, and then please ask me questions. Yeah. So I got the like there's a folder here, which I don't think I can go through it. So I asked for a list of questions, and then so this email is very, I mean, it's very good. Yeah, I didn't expect this coming from an MSc student. So so that's a compliment to start the day. Nonetheless, so it's very good. I mean, in the sense that this gives like a background information, and then what the problem really is, and then the whole list of questions, and um, this list of questions, if we look at that, if it's more like I mean, these questions are applicable for all kinds of process simulation software. Yeah, not only for Aspen Plus, but also for Aspen ISYS, Symmetry, Unisim, Petrosim, all kinds of similar process simulation software. And from I mean, compared to Aspen Plus and HYSYS, HYSYS means, I mean, the HYSYS, there's also like a unisim, petrosim, symmetry. These are four. These are all like the same method of doing or solving the calculations. But Aspen Plus is a bit different in a way. It works like what they call like sequential modeler. So I will explain to you that what that means in a minute. And then so it's about that. So it's a sequential modeler. I will explain about that. And then do we need to prepare manual calculation for mass balance beforehand? Not necessarily, but if you are like undergraduate or masters, it's better for you. Simply because yeah, chemical engineering is all about mass and energy balance. So if we cannot make that thing balance in terms of mass or energy, that means there's something wrong either in our model, the model itself, yeah, how the flow sheets are being arranged, or how we understand the process, yeah. So how the calculation and then how we understand the process. So it's a good exercise, but I think the more we grow, later on we will then see we will need for sure to do mass balance for overall mass balance, I would say. So input and then output streams. And then if you do the whole calculations correctly and then understand the process correctly, the input what is coming in, it has to be equals to what is coming out. And then that's how you make sure that the whole calculation is correct. How to choose fluid package? Fluid package is the other name for fluid package is thermodynamic model. So we learn thermodynamic model in not in thermodynamic one. I mean, in chemical engineering we learn about two. Yeah, I mean in most cases we learn about two types of thermodynamics. The first one is about the basic thermodynamics. This the first, second, and then third law, and then the second thermodynamic course, people call it like a chemical engineering thermodynamics or advanced thermodynamics, whatever. So that part of the thermodynamic model is the one that we are talking about here, the fluid package. So in that thermodynamic model, we learn about the phase equilibria. We learn about ideal situation, ideal gas, and an ideal solution. And then we learned about non-ideality, and then we learned about how people then try to approximate the non-ideal gas and then the non-ideal solution. So from these, yeah, we have like equations of states based thermodynamic models, and we have activity coefficients based thermodynamic models. So this is the thing that we have to understand a little bit. I know from my own experience that we don't put like a strong emphasis on this, on the thermodynamic, on that chemical engineering thermodynamic model. It's everywhere. So don't worry. But it becomes the basis before we do anything with process simulation. I will show you in a minute. In this one, in HYSYS, yes, and others, yes, I know how to do that. But in Aspen Plus, I don't know how to do that. We will see. We will see how we could do it. Yeah, we'll just explore. And then where's the exact part? The fluid packages function. So this question relates strongly with the question number 2. Any reason to choose it, and then where is it? I mean, what is it actually? So like I mentioned, it's a if you know the PV and RT, right? That's the basic of our ideal gas equation. The PV and RT, if we know, so we have like we have one constant, yeah, the R is one constant, and then if we know we have now variables of P, V, and then a number of moles, the N, and then T. So if we then can can specify 3 out of these 4. So the fourth one will be calculated, and then we'll be okay. So for example, if we know the amount of molecules in the system, if we know the volume and then the temperature, the pressure of that system will be calculated. So it's more about how to find the condition. So if we have like if we have like a two-phase fluid, for example, yeah. So then using this equation, we can then estimate how much then going to the liquid, how much then going to the vapor. So if we know how much going to the vapor and how much going to the liquid, so I think I will then, yeah, I will draw it so that it gets clearer. Yeah, so for example, if we know that the flow rate, and then we know the pressure, and then the temperature, and then we know the composition, and then it goes to liquid, vapor, and then it goes, some goes up, some goes down. So using that thermodynamic model, yeah, depending on the system itself, depending on the what is in the stream, what kind of components, what kind of molecules, and what is then the pressure and the temperature at which we want to analyze it. So these thermodynamic models, they have a way to predict, yeah, I say to predict how much is then going up as the vapor, and then how much is then going down as liquid, and then what is in the vapor, and then what is in the liquid. So so if we select a wrong thermodynamic, I mean, if we select thermodynamic model A, for example, it may predict that VA over here, and then the V and then LA over here. And then if we put like if you use a thermodynamic model B, so this thermodynamic model B will predict how much then the VB over there, and then LB over here. So they may not be the same, yeah. They may not be the same. It cannot. I mean, they may not be the same, even though they are, I mean, thermodynamic models. But depending on how they calculate that, depending on the systems, and then depending on which conditions that these thermodynamic models were developed before, so they may or may not give the same results in terms of how much is then the vapor, how much is then the liquid, what is then the how much then this is the A, this is B. So these may or may not be the same. The same way here, ZLA, ZLB, so they may or may not be the same. Yeah, so we need to be very careful. So from experience, not from experience, I mean, the original ideal equation, ideal gas equations, as you know, it's ideal gas equation. So that means this is only like dealing with ideal gas and an ideal gas, and then people then start developing. I mean, furthering the we have the PV and RT, right? So these then the ideal gas equations, and then people then start expanding this into more and more complicated in nature, because they found that not all systems can be modeled with these equations. Yeah. So for systems that are maybe, I don't know, take van der Waals, for example. So van der Waals says we cannot then treat, because these equations says that all molecules, because this is then the L, yeah, all molecules, either it is hydrogen or nitrogen, or maybe water vapor, or maybe methane, or C3, propane, and so on and so forth. They all behave the same. But then Van der Waals says, no, they're not the same, because all of these, they have a different size. Yeah, so because of different size, they may interact. So this molecule, say for example, this molecule and that molecule will not be interacting the same way as this molecule and then that molecule. So there will be like a different ways of interacting. Yeah, we cannot know for sure unless we see the experimental data. So from the experimental data that they have, they will then put the like additional term for this in such a way that they take into account the size of the molecules. So if you Google, for example, this is just an introduction, yeah, introduction to it. So if you Google, for example, Van der Waals. See, so this Van der Waals equation, it says that while we have a volume molar means V divided by molar. So they have this, it has this term. So it has the term on A and B. So the A and B is, if you look down, yeah. So the A is roughly the average attraction between particles. So what I meant here. So this interaction between one molecule to the others, which is approximated from literature, from the data, and then it has the measure of the volume with the B. Is the volume excluded by the mole of particles. So it is related to the volume. So you see this. So this guy will behave or will attract or will repulse different molecules differently than the other guy, than this guy. Okay, which makes sense, right? Which makes sense. So big guy will then be able will have a different force to attract or to repel another molecule, while a small guy will then have a different strength or so. So and then this is then the whole issues of thermodynamic models becomes more and more complicated, because they simply want to correctly predict more and more difficult system. So if you have now, because now we have from ideal, right? So we have the ideal gas, and then they have also like ideal liquids or solutions, and then the Rawls law, if you can still remember. And then they goes to like, okay, now if we have like non-ideal gas, but then ideal solutions, and then it's also like okay, ideal gas, non-ideal solutions, and then they have the most complicated one is then the non-ideal gas, non-ideal solutions. And then you can also see that more and more complicated, like a polymer, which includes the solid handling and stuff. So here the ideal gas, we can see that the ideal gas, that PV right? PV and then the Rawls law. And then non-ideal gas, we have like these activity coefficients, if you know, like Wilson, Van Laar and stuff, and Bang Robinson as well. So it's also non-ideal gas. And then you have like a non-ideal solution is you know that NRTL, Wilson as well. So those kinds of stuff. And then in here we typically use this univac, uniquevac, and so on and so forth. So I will show you how we can use because in process simulator they have like option to select which thermodynamic model is suits more than the to our applications than the other. Yeah, but still also, as you hope you understand now from here, it's more on approximation until we get the exact experimental data or results, literature data that is accurate, that is correct. And there's also like literature data that is not accurate. Yeah? So and then it can then help us to at least to guide so that we know that we can use it as the first step basically. And so that's about that. And is binary interactions affect the simulation process? I think you understand it already now here. So if we have like for example if we have like and then A and B. So there's a component A, and B, and then if it's ideal, and then A being the lightest, go here, and then B is then the lights in the heavy. In ideal gas, these two guys, they don't interact, right? That's the definition of ideal. So A is over here, and then B is over there. They don't interact. They don't like. I mean, they don't interact. Not they don't like each other. They just simply don't interact. So if they are here, they will just be there. Yeah, they will just be there. And then if they are some in other molecule somewhere here and then somewhere there, they're just simply there. Nothing happens. But then if we go into the non-ideal situation, right? In the non-ideal situation, I put like a red. So if this is then the A, so this A may we don't know. It may pull B towards it, or B may pull A towards that. So this guy becomes maybe something like this. That's one situation. Or maybe in one occasion as well, they don't like each other, right? We don't know. Maybe this A is different from that A, so they will then repel each other. So this becomes like something like this. So there are So there are some interactions between the molecules, and then like as I mentioned over here, so A will then maybe attract more B, right? And then maybe B is then not they don't like it, they don't. I mean, they simply have to be attracted to A simply because of their size and so on and so forth. So because of these interactions, say for example, this is then what is happening. Yeah, this is then what is happening. Say for example, this is what is happening. So that means we'll then have, so if A is then light, so we will then expect A over here. But then since B are attracted to A, so we will have more B. than it was in the ideal gas, in the ideal solution. So we'll have that more B over here. So we have A, and then we have also B. So I'll put like 3A to show that A is then lighter, and then B is then heavier. But then since B likes A, or A attracts B, and then B will be more in the B, there will also significant amount of B. I should say it that way. There will also significant amount of B in the vapor. So here maybe we have like a B, B, and then B, and then maybe like 1A, for example. Things like that. But then in the ideal situation, just to compare with you, in the ideal situation, we will have only like A, and then here B, B, B. This is what happens in the ideal. Maybe there's some A over here, maybe 1B over here, but the majority is like we have like significantly lower B in the vapor and then lower A in the liquid. But then if it's ideal, there is a tendency that there's a tendency that B will be attracted or pulled by A into the vapor, or and then the other way around. So having these situations occur, and then choosing the correct thermodynamic model will make us predict the situation much better. Yeah. So if we somehow use ideal gas or ideal thermodynamic model, ideal gas thermodynamic model, we will have this kind of result. While in reality, it may be like this. Yeah, it may be like that, which we don't know. Until we get that experimental results from reality, yeah, not metaverse. So from reality, we will never know. So again, this whole thermodynamic models, it's just model. So model is it's just a simplification of what we think of reality is. Choosing the correct one will help a lot. Choosing incorrect one will then destroy the whole analysis. And then this binary interaction is what I mentioned before, that the interaction between each molecule. Effect, yes. So Aspen Custom Modeler. Last time I used Aspen Custom Modeler was in 2008, 2009. So it's 15 years ago. So I'm not really sure how to do that again before we go. I mean, we can just look for help or whatnot. Yeah. But then I would want to see what do you want to I mean, what is it in this membrane reactor that you want to model? That's number one. Because we know all of this. So because we know so process simulation, the way we it's more like a conceptual process design basically, or process development. So we develop process. Again, this is also not conventionally taught in the undergraduate or master's program. So process development, we have to think in functions. So we have to think in functions. Think in functions. So what I mean by this is that, so for example, molecule A and molecule B become C. So what functions are we now seeing here? So here we could say that, well, the function is then to mix, right? Because if they don't mix, if they don't meet, nothing is going to happen. And then once it is mixed, it will then be react, all right? Yes. So A and B, they have to meet in some place. So this place, we call it catalyst typically, or surface active. Right? So they have to meet. So it goes here. So A says hi to B, B says hi to A, and then they meet and they make a child. Well, that child is C, right? So they make a react. And this C, it has to be, maybe there's also like A somewhere here. There's also like B somewhere there. And then this C, we have to be able to separate that from the system. So we separate that, right? So we do like a separation. So there are three functions. So from these equations only, we can think of three functions. Number one, we have to mix it. Number two, we have to react it. Number three, we have to separate that. So membrane reactor The reactor itself has these functions, right? The reactor itself has these functions. Well, this is primarily the functions of the reactor, but it has to have these mixing functions as well. I mean, they have to mix so that they meet. And then the separation, it can be done downstream of the reactor, or it can be done in the reactor, which we call here this membrane reactor, or the process intensification unit of the membrane reactor. So so what happens in the membrane is this is something, the mechanism of the separation in the membrane is something that you have to understand. Yeah, I don't have a full understanding on what type of membrane that you are using and then how it separates the products from the others. Yeah, the products that you want to know. So simply, for example, yeah, just take example. I don't know. So maybe we have like this in the wall, this in the wall. Right? So we have like A is then over here, it goes there, and we have A, and then we also like a B, I don't know, B somewhere here, it goes here, and then they make C, right? And then this C is then if we have more C, so we have like a higher pressure of C on this wall, and then there is this there's nothing here, there's nothing here, and then it will then try to, I don't know, either diffuse depending on the type of membrane, like I mentioned to you. So it's about like a reverse osmosis of type of membrane. It will then diffuse. It will then diffuse. Yeah. If it's like a nano size and then the bigger than the nano size, like a micro microfiltration, so whatnot. So it will then penetrate through the holes. Yeah. So depending on what type of membrane that you're using, how the mechanism, it may or may not be. I mean, the equation that we put may be different. So if just like a diffuse, we have this fixed law and stuff. So it can go there, right? So depending on the pressure difference, between this here and then outside of the wall. So that's the how the mechanism works for the membrane. So the idea is that maybe in this case you will have like a equilibrium reactions. I don't know. So once you get the C, you want to take that C as much as possible in such a way that C doesn't come back to A and B. Yeah, it could be one of the reasons. I mean, it's typically the reasons why we do separations and reactions at the same time, right? So, but we need to make sure that that the membrane itself has a higher affinity towards C than B and A, and then the catalyst is then on the surface or somewhere. Maybe this is like a fixed bed reactor. I don't know. Yeah? So something that you have to be able to explain to me. So, but then the modeling here, how to model this. Um, there are many ways to model this. Number one is then we have to ask ourselves the question is what do we want to know? Do we want to know the size of the reactor? Is that what we want to know? The length and then the diameter? Is that what we want to know? That's number one. Or we want to know how yeah, like for example, the type of say for example, we have a different type of membrane reactor, yeah, membrane reactor 1 and then membrane reactor 2. It has this, like for example, I don't know, separation factor, I don't know how you call it, and then delta P, and then and so on and so forth. So if they have like a different maybe 9 or 10, and then maybe this 5, this is 1, I don't know. So it has, if it has different performance, and you would like to see in a detail as well to see how the things affect the situation in the reactor. We could go into details, but I'm not really sure. Do we have to go into details or not? Do we have to go into details or not? Because you could do these calculations how to explain this? Yeah. So you could do it. What I would typically do is that because this is like a function, so we have like a reactor and we have these separations, and then this separation is a functions of operating code design, right? The design of the membrane, and then the operating of the membrane. So this design operating of the membrane, these are the table that I put over here. So depending on the what type of design and then what type of operating conditions that we allow it to happen, it will have then the different separation performance. So these lines over here. So if we have a different operating conditions, different design conditions, it will have a different separation performance. If we allow it to happen, it will then we could do it in so many ways. Number one is that we can just simply use like some correlation, some models in such a way that it will then if we input this, input that, and then it will then calculate the separation performance. That's one way. Or we can simply do it outside of the simulation model. Means we select a certain design of parameters, a certain operating parameters, and then we know what is then the performance of the unit. For example, that performance of unit, for example, is then the recovery rate. So I know that 99% of my EC will be recovered, and then A is then like 10% or 20%, and B is 10 or 20%, and then those numbers we put it into the model. Yeah, so we don't model the reactor, the equations of the reactor. We just simply model the separation performance. Okay, so one is then the model the membrane reactor in detail, and then two is then the model model the separation performance only. Okay, so you can then choose, right? If we model this in detail, depending on how much detail, depending on how much detail that we want to see, how much detail that we want to model, yeah, we could do it in many ways. I mean, we can in HYSYS you can use a spreadsheet. Right? So this spreadsheet is basically Excel. So if you can model this in Excel, if you can model this in MATLAB, means you can model this in Excel or the other way around. I mean, Excel is the easiest. So if you can model this in Excel, means you can model this in spreadsheet of HYSYS, and then you're done. Or you could in Aspen PLUS. I think in Aspen PLUS you can model this in calculator block. If you can model this in calculator block, and then that means you're okay. The same way in I don't see there is a need to model this in MATLAB and then make the connection with Excel. This Aspen PLUS. The Aspen PLUS, and then the Excel or whatnot. So this is I don't know how to do this, but there are people who can do this. Yeah, I mean you can look it up online. But I don't see there is a need to go into this level because there's so many interface between the software. It will then create a lag or delay and then the data transfer, and then you want to do I see that you want to do also like a more analysis in the techno-economic part, so it will then create another hassle down the line. If you want to do that, fine, but well, you can. Yeah, I mean it's up to you. I'm just showing you what's possible from my perspective. So you could do this, and then this one as well, you could do the same thing. So in you can use like Excel or spreadsheet in HYSYS, and then you could use a calculator block, an Aspen PLUS, and then there's no need for MATLAB or whatnot in this performance only based, because it's simply like it is straightforward calculations. So this is about what's that stuff? This question. Do you need? I don't see there's a need, but if you want, you can. How to put Aspen custom modeler in Aspen PLUS? This is something that I also don't know. This one I don't know. How to put Aspen custom modeler into Aspen PLUS? Yeah. Is it possible to Aspen custom modeler? Yes, always, of course, possible, because Aspen custom modeler is just like its name. It's customized, so you can model the membrane in Aspen custom modeler. And in fact, you could model the whole thing in Aspen custom modeler. So you can start building flash calculation, pumps, heat exchangers, distillation column, and so on and so forth. You model it yourself, and then you can then have everything in Aspen custom modeler. And then the last one is new to us in Capcos. Yeah. I don't think US demand energy in Capcos. In cap cost you can estimate the cost, but it's very manual, right? So you have like one flow sheet. You have like one flow sheet. Say for example, very simple one, yeah. I mean the heat exchanger typically, you have a reactor, you have a flash, and I don't know, something like this, right? So you have three equipments, heat exchanger, reaction, and then distillation column. So you have three equipments, and then in the cap cost, say for example, I don't think we can go into more on the technical economic analysis, but I will give you like a basis on how to think. So now we have, say for example, it is A plus B makes C, A plus B makes C, and then you have why do I want to recycle? Maybe I don't know. Maybe A is then the so this then the A, and then this is then the B, B, and then this is then the A makeup. A recycle. For example, that's why I put this recycle. And then this A contains like I don't know, maybe D, and then this is then the D that you have to remove. Okay, so we have C over here, and then B is then consumed, and hence we have like a B makeup lot more. So in here, so you have like one scenario. And in this flow sheet, you have to specify base case. So base case number one, make a base case. So this base case, you can define it as you wish, but typically we use like the current state of the art, process. So the current state of the art process typically like we know what is the pressure here, we know what the temperature here, and obviously we will then supply the duty in such a way that it will then give the temperature as required over here, right? And then it has the certain conversions. So you have like a reaction kinetics, right? The reaction kinetics, and then it has a specific like for example we have a reboiler as well over here, just to keep it very simple. So we have a reboiler, we have a condenser as well, right? So we have 1, 2, 3 energy related duty, and then yeah, that's it basically, yeah, for the simple. So this state of the art, or conventional, your best case. So in here you can say now I have because this is then your independent variable, the t, from here. So if you specify t, you will calculate q. If you specify q, you will then calculate t. So whatever you want. So so in this case, say for example, for the sake of simplifications, you specify temperature, and then you specify the now I don't know which one you have. Do you have kinetic reactions or you have the conversions? But if you specify temperature, it will then indirectly or directly even, it will then control for you the conversions and or the reaction rates, yeah, conversion and reactions also. So this one, in this case, this is then your main control. But then also over here, you could also have like a reflux, for example. I just want to have like another variable. So reflux. So this reflux will then control the purity of the C, the purity of the C. So now you say, okay, now I have, for example, there's two ways here. So the 2A is then, so now you have another. So you have a different T2, and then the reflux 2. So this T2 and reflux 2, obviously, it becomes like the first modifications, right? And then in the base case, I forgot. So this base case, you go to cap cost. So in this, you get to cap cost. You go to cap cost, you get that capex. Yeah, the whole how big is this? You have to split based on this mass. So from this simulation, you get your mass balance, mass and energy balance, mass and energy balance. So from this mass and energy balance, you can then size it very quickly, size. And then from this sizing, you can then go to cap cost. You get capex. And then for the energy, you can then go for the opex. Yeah, and then you get your like annual cost, for example. Or if you want to go for investment as well, it's also fine. And then you can then get your NPV or IRR, and then the payback period, and then you do the same for the for this. If you do one modifications, you have the different temperature, and then you have the different flux ratio. Yeah, make sure that you fulfill the sales criteria, and then you can then go to the same thing. So you go to you get the mass balance, you size it, and then you use cap cost to calculate the capex, and then calculate the opex, and then you do this, and you will have like a TAC1, and then you have also TAC2, NVV2 is 1, and IRR2 is 1, and then payback period 2 is 1. And then you can compare. So that's one approach. And then you can then play around here how many temperature, how much temperature, how much then the reflux ratio, and then you can then vary how many variations between them. But you could also do, in your case, I think, which is more relevant, so then you have a different membrane, right? So now you have, like, for example, and then this A, and then you have a heat exchanger, and then you have a membrane reactor. So this membrane reactor, somehow you have your C. Sorry. So this is your C. So you have your C, and then this is then your A and B. A basically A, right? So you push A and then D, and you put back A over here, and D, and then you have your B. So this is then your system. So in this case, you will then pay something with this exchanger, which is the same basically. Well, roughly depends on what you see later on. And then you have the advantages of having only one block as compared to reactor and then distillation column. But this one block, be careful. You will need to calculate the cost also carefully, because some of these unit operations, even like if they are like new ones or not conventional unit operations, the cost may not be as accurate as what we could find or compare with the cap cost, the one from cap cost. So there is something that you have to think about. But then once you get the capex and then opex, you can do then the TAC to B, and then NPV to B, IRR to B, and so on and so forth. So you can then compare and then see whether this makes sense or that makes sense, or well, let's just stick with the old one. So it's something that you have to see. So the idea now, because you mentioned about cap cost, how to approximate or predict the or calculate the cap cost, the capex, right? So I'm assuming that you can do sizing correctly, yeah, because if you cannot do sizing correctly, and then forget the whole cost calculation. So so this one at Aspen, the current versions they have already, which I think will then help you a lot now, because doing this caps cost is more like a manual, right? So you have your full flow sheet, and then you size it manually, and then you put and then these are like an Excel file in itself. So if you don't get the equations behind it, and then you'll then it will be very difficult for you. But nonetheless, you know that this is more like a manual and then laborious effort. So maybe you can do, like, for example, if you have like one flow sheet, you could do, I mean, you get this after 1 week or something, right? So a few days. And then you make another modifications, and then you will get another this capex, another 1 week. So in like 1 month, roughly, you'll get like about 4 cases only, right? it's 1 month. If you do it very systematic and very consistent, and then you do it right. So it's about 1 month. It's only like 4 alternatives, but which is very laborious, yeah. And that's the optimistic case, yeah, because it's simply for undergraduate this, then your first experience to do this, so it will for sure will take you, instead of like 1 week, it will take you like 2-3 months. But nonetheless, with the current versions of Aspen, they have what they call like Aspen. I think I open it somewhere. Let's see. So you have you have this capital and utility cost. Capital and utility cost. This is something that you can leverage. You can use it. Later on, you will see what is then the basis of this. You can go to help, and then I think we can see it quickly later on. So you can use this. You can use this, and then you can then because at this point in time, yeah, at this point in time, this is what we call like the very early phase of R&D. So we don't really care too much on the accuracy. What we want to have is the constant constant like a comparison. So it's you have like a base case comparison, and then the whole cost calculations based on the default method of sizing by Aspen, and the default method of estimating capex and opex for Aspen. So even though they are not completely correct in absolute sense, but if we use the number, to compare this, to make this to compare, and then to compare, it's good enough. It's good enough, yeah. So in that sense, you don't report this. You don't report this. We don't report. So now we'll have to just to make it. So now this then automatic calculations. So this whole thing becomes automatic calculations, right? So they go here and they go there, and then they go membrane reactor, they go here. So you do automatic calculations, and then in this case, you don't report the TAC, NPVI, blah, 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 right? We don't report that. You calculate that. It is being calculated, TAC, IRR, NPV, payback period. You calculate this, but what you report is then you have a base case number, right? And you have 2A and then 2B. So what you do is that how much is this compared to base case? So BC, I don't know, BC, TAC. How much is this? Like 90%? Or this may be 110%, I don't know. And then IRR, for example, TAC, the base case, sorry. I do it. So this would be like TAC base case is then IRR base case, and then you can then see, okay, this one is then the, I don't know, maybe 101%. This is maybe 95%. I don't know, yeah. So this is the things that you have to report, yeah. Not this. This is not what you report. You calculate this, but then you go one step further. You compare only how much is this compared to the base case. So that's why selecting the base case is very important. Selecting the base case and then do it right is very important for all techno-economic analysis. Why we can they maybe ask yourself, well, why don't we also do the same? If we use cap cost, why don't we just do the same instead of stopping here? We can also do the this kind of evaluations. Well, you could, yeah. It's not stopping you. Just like cap cost is based on it's based on the book, right? And that book is then based on historical value. And then that historical value is also like very old as well. Yeah, it's very old as well. It's not like a recent. And then depending on where we take the cost, I mean, the cost is based on US Gulf Coast, or somewhere in Middle East, or somewhere in Asia. So depending on the years as well, depending on the type of equipment as well, it may or may not be accurate enough. So the safest way to do, indeed, the safest way to do to report the results of a techno-economic analysis is then to compare the economic values based on this. So that's the economic part. Yeah. So techno-economic is I'll compare this. Techno-economic is my pen.
Doctor, I have a question, right?
Yeah.
Let's say membrane reactor is basically a new unit. the
Yeah.
one that we are model. So it must, I mean, like the data in terms of the cost should not be available in the
Yes. Yes.
as per. How do we do that? Because I remember last time, if we want to do like membrane reactor, normally we try to do like a reactor, a fixed bed reactor, and a separator, some sort of like that, like just
Yeah.
to roughly get the cost. But what is the best way to get like some sort of like accurate value, or not accurate, but near value for that
Yeah.
membrane reactor?
Yeah. Yeah.
What is
Yeah.
your
Yeah.
opinion on that?
Yeah. Yeah. Very good. Very good. So the best way that we can do is from the material cost. Material cost. So this material cost, if you know that if you have that the membrane reactor, you have the catalyst, right? So that means you have to then I don't know, it's where I don't know where the catalyst is located. Yeah, it's you may help me with that. So the amount of this the amount not volume, the amount of the catalyst you have to know, and then this serves for the specific conversions of specific conversions that you allow, right? So these specific conversions
Okay.
that you allow. And then you can calculate the mass of the catalyst. And then from here, I know where you design the, say for example, yeah, for the sake of this is just from my imagination. So this is then your the membrane part, right? So this is then your membrane part. So you know then the length of the membrane, and then the diameter of the membrane, right? The diameter of the reactor as well, and then how to put this membrane in. So how big is then this membrane? So catalyst cost is easy, yeah? Cost is relatively easy. Cost is easy. Okay. But then the for the membrane itself, we need to know the material cost. Material cost. So from this diameter, it goes to the material cost. This is also the material cost. And then the material itself, membrane material is going to the cost as well. So from this material cost, and then you can then assume, so this is only like a cost, and you can assume how much is then the, I think we can look into the literature, how much is then the like a fabrication or manufacturing cost. Just use a reasonable how to put it, yeah, reasonable factor cost, and then like installation cost, and so on and so forth. There are like rule of thumbs, but this rule of thumbs are really different. I mean, they are only based for certain how do you call it, for certain like or conventional applications. So from the conventional applications, we have something like so from this material cost, we typically multiply it by 3 until 7 times. Say for example, your material cost is then 1,000 USD. I don't know, yeah. And then your then the membrane reactor will be like 3,000 until 7,000 USD, and then plus catalyst. This is the thing you have to put. So this is how we approximate that. But then I think this kind of approximation, you just have to use. I mean, base this on the, please base this on the like a literature. Because this is like what we've done internally, in one of the companies. So this is then the numbers that we keep seeing. And then, but I'm not really sure if these numbers have been reported in the in literature, but I think it has been reported in if you go for yeah, in our time we have this chemical engineering design volume 6 from Colson. Now it's I don't remember what that book again. 1 minute, yeah. Chemical engineering design. Toller and Synod. So in this Toller and Synod, I think there is something there's something in it. Yeah, I have to look it up. There's something in it that we capital cost estimating. on I mean what kind of factor he uses to approximate the cost of the equipment, and then compared to the material cost. But for sure, the basis that we use, and so I mean, it has to be the material cost. Once we size this correctly, we know how much then the material cost, because we know on the thickness and we know the length and the diameter and so on and so forth. We can then calculate with the selected materials. We can calculate the material cost. That is, I mean, we cannot bargain or argue with this number, right? This is a fixed number. We cannot buy a platinum vessels with the carbon price. We cannot do so. If it's a platinum, it has to be like a platinum cost. It's a palladium cost. It's like a carbon cost. It's carbon cost. A steel cost. It's steel cost. But that is something that we cannot bargain for. So this is a fixed number, and then we either multiply to 3 and 7. It's depends on how difficult this is, or maybe how early this is in the stage of development. For example, if you say, for example, well, this is already like a well-known, there are many manufacturers using this, and then we can safely say, well, it maybe tends to either 3 to 4 because there's so many competitive manufacturers. You can do so. So this material times 3 or times 4. But then if you say like, well, this is a very early stage, only like one, maybe or two manufacturers in the world that know how to use this, and then we have to use like either 6 or 7 times the cost. But this is something that you can use for the techno-economic analysis, because that is then this part that I want to show, the techno. People tend to use techno-economic analysis simply that they make the flow sheets, and then they report the cost, and then they say done. That is not the correct approach. Yeah. And then, well, we see that in papers, but the correct approach is that because all of these things, these are technical stuff. These are technical stuff. This is something that we can report. So if I go back, I mean, just stay here for a minute. So if we say then the technical part of the analysis is that, say for example, the material cost is very high. So how much is then the NPV? How much then this guy again? If the material cost is high by 10% or by I don't know, plus minus 10%, for example. But this is something that we can play around. And then if say for example, well, we're not really sure if the performance of this reactor, right? So for example, if we have to replace this by replacement by once a year, I don't know. And then how much is then the TAC and PVI period for this replacement once a year compared to like 3 years, once in 3 years. So this is something that we need to evaluate. As well. For example, if we then use a different catalyst, right? Different catalyst, will it then tend to produce more C or less C or something like that? So if we have like a default catalyst, like a base case catalyst, and then if we compare with the new catalyst, old versus new catalyst, so how much that it affects the whole economic performance. Yeah. So this is like 3 examples that I can think of right from the top of my head now, to say, I mean, the technical part of this, how it affects the economic performance of the system, because at the end of the day, we will have to be able to answer because it's all about money, right? It's all about money, so we have to be able to answer with this kind of numbers, taking into account all of the variations that we have had before, and then the possible combinations that we can think of in such a way that we are sure that this alternative proves to be better than the base case. I have something as well to I should have written this in a PowerPoint, but nonetheless, say for example, now come back from the flow sheet, another aspect, yeah. So I've shown you the techno-economic part. The techno-economic part is done. Economic part is done. So there's another aspect of this techno-economic. So we go for here, reactor. Satu membrane reactor. Now you have a base case, right? Number one is base case. Number two, operating change. Number 2A, and then 2B is then the membrane reactor. You can also have like a number 3. So what is number 3? And there are many lots, yeah. It's just an example. So say for example, now, well, we have, for example, we have like a total capex, right? Capex, and then opex. And then in these parts, we have like a heat exchanger, and then we have the reactor, we have the distillation column, and then we have heat exchanger, we have the membrane reactor, for example. Right? Option 1, option 2B, for example. Now, from this capex, you can say, well, this is only like a 10%. This is 30%. This is a 60%. Right, and then this is also like 70%. This is well, because of catalyst replacement and whatnot, is 20%. This is 10%. I don't know. Okay, and then this then so we said the capex is maybe is like 30%, is 70%, and the opex is about I don't know, maybe the same 50%, 50%. Okay, now you can see in this case. Say for example, look at this number 1, right? So in terms of the capex, we can see this guy is consuming a lot of money. This guy is consuming a lot of money, right? So why is this consuming a lot of money? There's something that we can think of, right? Why is this consuming a lot of money? Maybe because we are now, I don't know, maybe this is it has a very, well, very difficult separation between C and B. I don't know. CB is very difficult. Oh, yeah, CA, because A is then the recycle. CA is very difficult. So we will need more trays, for example, right? So that could be the cause for this. We will need a bigger distillation or a taller distillation column, or maybe we'll also need like a more energy consumed because of this, for example. So then we can think of, well, is this then really necessary if this membrane is there? So why don't we just put instead of number 3, instead of DC, will then be replaced by membrane. Not necessarily you have the membrane reactor, but you have a reactor and then the same membrane. All right. So this is then your number 3, because this membrane, then you can then borrow, okay, it's not so much of an operating cost. We have a pumps only. It's also like not so much of structure and so on and so forth. So this could become the third option, or another alternative. Yeah, just to think out loud. And then the same exercise you could do for this one as well. So then we can say, well, this guy consumes a lot of energy. Sorry, a lot of money, but the energy is about the same. I mean, the cost is about the same, the capex, but then it's consumed a lot of money. Why is this consuming a lot of money? You could then say, well, there's nothing more that we could do. It's just like this. Then it's very close to the material cost already, and then there's nothing more that we could do. But you could also see, yeah, I don't know. You could also see later, maybe, well, the operating condition is very severe, so then we need to have like a very expensive alloy for that. So that could create this number. So what if we can then find a better catalyst in such a way that it will then run in the same performance at a lower or less severe conditions? In that way, we can then reduce. We can use a cheaper material, and then this number will drop down to, I don't know, maybe 60% and then 40%, yeah, something like that. So it's something that you can and then the MR becomes a new material, cheaper material. So all of this is coming from the techno analysis, not the economic part. Is techno analysis, and then it will then give you the economic performance. Okay, so all of these things, I mean, practically speaking, we need this number, but then sadly, we don't see this analysis in journals or textbook, because maybe people think of this like it's a no-brainer. We have to use this. We have to do this anyhow. But nonetheless, this is the kind of techno-economic analysis part that I see often missing. This one and then the previous one, which I don't remember what was that again. So up until here, we spent like an hour already without touching Aspen Plus. Just simply answering, trying to answer this question. Is there any questions before we go to the Aspen Plus, or any question?
Doctor, I have a question.
Yeah, please.
Just now you mentioned that we can model the membrane reactor in Aspen Plus only by using calculator block. Is it? But let's say if we and we can model in terms of maybe in detail or performance of the membrane reactor kan?
Yeah.
But if we have the details of operating condition and the kinetic equation, do we need to model the membrane reactor in detail or just the performance? Or is it depends on us to model what type of membrane reactor?
Yeah, it really depends. It really depends on you. It really depends on you. The way I see it, yeah. So we can if you have like a now say what you have reaction kinetics, right? You have reaction kinetics. You have the membrane performance, right? So you have kinetics. You have reaction kinetics and then membrane performance. These two things. In this case, you can so you can have like a kinetic reactor. So we have the kinetic, right? And then you can then after this you can model the membrane itself. So the membrane performance, I don't know, it depends on yeah, I don't know how, I haven't seen the equation. So just put delta P. I mean the delta P. Sorry, performance is a function of delta P, for example. Yeah. So and then this then your yeah, you know, it's a functions of temperature, right? So in this case, this one we model in like like a plug flow reactor, right? And then this one we can model in like if you have this, if you have these equations, we can use like a calculator block, or we can use spreadsheet, depends on where you want to model that. So that's one. But then you could also say, if I don't want to model this, right? The second option is then we have the um, reactor model, and then we can also like a component splitter. So the performance is also a function of delta P. But this delta P, you don't, I mean, we don't, this doesn't become the input to the Aspen Plus model. This becomes an input in your own calculation. So you have your Excel calculation file, where you calculate, you have inputs. One of them is then being delta P, and then you have outputs, which then the performance. And then you can then say, well, maybe 10, I don't know. And you put this 10 into this guy. So you no longer use this, but you put 10 into this and then maybe display like 10%, I don't know, maybe 10% over here. And it's then 90%. Yeah, it's something that you can do. And for this one, you have the equations, you have the whole equations model. You put it there. So it's really up to you how you want to approach this. But then in the end, because this performance, these equations, it depends on the design itself, right? The design equations and the operating equations. So this strongly related to the techno-economic analysis that you will do later. They are strongly related. So if you change the design, what does it impact? How does it impact the economic? If you change the operating conditions, how does it impact the economic as well? How they are being modeled in the Aspen Plus or Aspen HYSYS, it's really entirely up to you. But then how they are connected to the techno-economic analysis, it has to be clear. We will use an example later on in this case. Hopefully we can have some time. Any other question?
Hello,
No?
doctor. Hello, doctor.
Yeah.
Regarding the economic analyzer, right? Is it the payback period and the NPV can be calculated by using the Aspen economic analyzer, or we need to calculate it manually?
Oh, that one I don't know. That one I don't know. Well, I would have to see. We'll have to see. I understand there is a report that we can generate, but I'm not really sure. I think we just simply have to make a flow sheet and then take this and then see what happens. This one, I don't know. You just have to look.
Alright. Thank you, doctor.
Okay. Anything else? If not, then we can. You have your Aspen Plus, right? I have this Aspen Plus version 12. Well, it's the same. I don't know where this feature comes in. I don't remember, especially this capex and opex, capex and utilities. So I'm not really sure. I don't remember. Is it Aspen 10 or 11? That one I don't know. So that nonetheless, you have to once you open this, you will get this kind of window, and then you typically go to the properties before, right? And then in these properties, the same like ISIS and the others, you will have to then add the component. How to add the component? The easiest way is then to use this find to find components, and then you can then say, well, what components do you have? Yeah.
6 component.
Huh?
6 component.
Yeah. What are they? So in this case, this water. So because this is the water really, right? Because if you use contains, you will have a long list of components, and then you may miss it. So just use this equal, and then click find now, and then hopefully it's there. So it is there, and you can then click add selected components. So water is basically there, right? So water, conventional component alliance is then H2O, and this is then the gas number. Yeah, make sure that the gas number is correct. And then what else?
Hydrogen.
Say it again.
Hydrogen.
Double click, and then if you double click, it will then say, strangely enough, it always replace, because we don't want to replace. We have to click add, but be careful, yeah, don't press enter or space, otherwise it will then replace. So you have to use mouse, click add, and then
Dimethyl ether.
Okay, and then
Methanol.
Then
Carbon dioxide.
yes. What else?
Carbon dioxide.
CO2. And then
Carbon monoxide, CO.
And then 6. Oh, 6. All these 6.
Yes, all these 6.
Oh, okay. Here you can see. So this is the Aspen Plus. So as we know it, so it gives you like this very strange names, right? So what I typically do, I will then rename this as H2, and then rename, and then this dimethyl ether is DME, and then methanol, methanol. This is CO2. Name this is CO. Name. So okay. So you have specified the composition, and then you can go number one. Once we know this, and then we can go to the methods. The methods then where we select the property package or the thermodynamic model. You go to the specification. You go to the specifications. I think I've selected like a chemical metric units and so on. So it goes to this NRTL. It has this method assistance if you want to. Let's see. Now this, say for example, you have a component type, process type. Say for example, you have a component type, and then it's like it's a chemical system, right? It's not hydrocarbon. High pressure. Is that at high pressure? What's the operating
Yes,
conditions of the
pressure.
reactor?
Yes, high pressure.
How big is the pressure?
In the range of 40 to 80 bar.
Okay, so it's then above 10 bar, so it says yes, and then in here it gives you this kind of blah blah blah. Mixing rules is also very important, yeah. So different mixing rules will give you different results, even though you are using the same thermodynamic models. Need to do blah, blah, blah. If you don't have any better, use this guy, and then for refrigerant, we're not using for refrigerant, and then you can then use either one of this. So and then you can so this one is then this guy, and then these options are, I think, all of this below. All right. So all of this I don't really understand except for NSK, SRK, and then PSRK, and then we'll see what this is. Yeah, then PSRK, then with this one mixing rule. So we use in this case PSRK, yeah, yes, PSRK. We have so in this case it has this base like NRTL and so on and so forth, right? But then in the method you can have a long list of NRTL, right? So you can pick one. So if we say that PSIK, now you have to want to use PSIK, and then in this case you can then see PSIK with you can just use this guy. It's no longer PSIK, PSIK, and I think this should be okay, right? Like I mentioned, the results may or may not be accurate, especially from the I mean, if we see from the thermodynamic point of view, but until we know until we compare this to the data from literature or data from the experiments, we cannot be sure. Yeah, so these two. So three even. Number one is then the number one is then the data from the experiment. Number two is then data from the literature, if there's any. And then number three is that your own common sense later on. I'll show you what it means. And this number three is also like yeah, I will show you what it means. It's difficult to explain now. And then you have selected the methods. You have selected the methods, the thermodynamic models. You could also use these parameters. It says this required input incomplete because it will still need us to get the binary interaction parameters. Yeah, the binary interaction parameters, and I would want to show you this one. So because we are using PSRK, for example, and then you can search for PSRK. Right? No. And this is PSRK. Why is no? Mixture type. Yeah. So you can use PSRK for mixtures for non-polar and polar. You have water, so you have like a polar, and then the light gases. One minute. So this one, I was looking into the equation so that I can say, okay. So I don't know if you can still remember this guy. So the RKS SRK is this is the SRK equation basically, and then you have all of these long list. To calculate this, you will need to be able to calculate A, which is this guy, and then A itself is the concentrations, and then AI, and then AJ. And this depends strongly on the Kij, which is the interaction parameters between component A and then component B, or component I and component J. So these are two different components. And then A1 is then the constant here, but then A0 is the calculated, and then there's also like okay, this A1 is in over here, and then yeah, long list of equations, which I also don't know what this means, but it's not it's not something that you will need to, if you want, if you like to delve into this thermodynamic world, you can go ahead and then calculate this for yourself, yeah. But so at least we have it here. We have it here, for example. Now we need to go to this red one. So either you go to this red. If you see there is red, you have to go to the right. Otherwise, you go to this next, because this next will tell you, or it will lead you. It will lead you to the next phase where you have to. So next step, you have to enter your number. So you go here. It will go to this. See, you go to this. So it gives you this binary interaction parameter for water against hydrogen, which is this, and water against CO2, which is this, and then hydrogen against CO2, that one, and so on and so forth. You can see this, yeah. And then it also requires you to just tick this, there's no need for you to enter the values if you don't have ones. Just tick this. Once we tick it, it will then retrieve the values from the database of Aspen PLUS. So you tick this, and then see, it becomes blue, and the values are keyed in automatically, and this one as well, NRTL. This NRTL simply because we have selected NRTL by default, so it is there. So we just have to simply tick it. And then it should be okay. Okay. This one, I think, yeah, here regression information. You can see it here. For example, if you select water and methanol, so it is in this data bank. I think I can show you where this is, and then these numbers AIJ, AJI, BIJ, BJI. This is on the NRTL. Let's see NRTL. We don't see NRTL. This one is just to give you an example. Yeah, if you go to NRTL. Oh, NRTL is not equation of states. This one. So this guy. If you see this, now just to give you a quick thermodynamic course. We have AIJ, AJI. So AIJ, AJI is somewhere here. This one. AIJ, AJI. Is that AIJ? This one. So AIJ, AJI is the same, yeah, just like you have a J and then I. And then we have then B as well, which is this one. We have C, which is this one, D, and then E, F, J, and then and so on and so forth, right? So it's all here, and then they are all see, they're all based on data regression, and then now here the A is over here. You see, AIJ, and then we have BIJ, and then EIJ, and then FIJ, DIJ, and then CIJ. So all of these numbers will be used in these equations, and then these equations will then be used to yeah, to calculate this alpha and then tau, and then this alpha and tau will be used to calculate the G, and then this G will be used to calculate here. Right, so here and there and there. So if you have the concentrations, and you have the concentrations, and then you can then calculate the activity coefficients. So basically, this is basically what these numbers are used for. Okay, so I will show you like let me see here. So I'll show you, for example, yeah, like you want to see the VLE. Say, for example, you want to see the VLE. So you go for binary, and then say, for example, you want to see temperature. So because you have a you'll separate dimethyl ether from methanol and water, right? So for example, and then dimethyl ether is then the lightest, and then water becomes the heaviest, and then methanol is somewhere in between, right? So I'm assuming that So we have DME and then methanol and then water. So we need to make sure that DME and methanol, they are the VLE data is or the VLE data matches the experimental data. So if you go to DME, for example, in this case, and then methanol, right? And then you have like more fractions of DME, for example, because DME is being the lightest, and then adds, for example, 1 atmospheric, and then you run the analysis, and this is using which equations? I don't remember. It's somewhere here. So let's close this again. Calculating options. So it's using PSRK, yeah, by default, because we are selecting PSRK, and then you can run this, and you get this. So you have the from 0 to 100 of DME in liquid, and then it says here this is then the liquid saturation line, and then this is then the vapor the saturated vapor line, liquid vapor saturated vapor line, and then saturated liquid line. Okay, so DME and methanol, which is a very nice separation, I would say. Now, if you go to say for example, DME, methanol, vapor liquid equilibrium. Assuming that this is the data you have from experiment or something. Yeah, this one, right? Is can I see this? Can you get this number? I don't know. Yeah, can I get this? No, I cannot access this. I don't know if you can access this. Let's see. I go typically to like in this case, Dortmund data bank. Or you can see on it there. You can see images. This Dortmund data bank. You can see this Dortmund data bank. Dimethyl ether. I want to see dimethyl, not diethyl. Anyhow, go to Dortmund data bank. In this case, this Dortmund data bank. If you see that stuff, yeah, Dortmund data bank. There is a place somewhere where we can extract the data, free data. Yeah, this is something that we have to. I don't know how to find it now. Go to here. Nah. No, I don't know. Elevated pressure. Yeah. Let's see if it has something. or CO2 DME. CO2 DME. Not mention each component, but nonetheless, anyhow, if you have something, I mean, if it has something, if you can find a way here, because I know there is a way, but just I don't remember that way. That is the problem. Resources. Nah. Thermodynamics, thermodynamics, search. This is the one. So very good. Methanol or dimethyl ether, methanol. What do I just say? Yeah. Or dimethyl ether is not here. Yeah, well, I'm about to show you the how to find some data so that you can compare it with the simulation prediction. For example, methanol. Methanol water is there, but methanol DME is not there. Water. Nah, there's nothing. Only diethyl ether. Yeah, okay. It's not there. So yeah, so it's a pity. But you could also do one more thing. I think you can go to NIST binary mixture. Yeah, NIST binary mixture, and you want to evaluate the DME and methanol. Yeah, DME, methanol, DME, methanol, and retrieve data. It will retrieve data from the NIST database. Yeah, why don't we search for NIST? I don't remember why we don't search for NIST. Now we want to see, this is then at 1 atmospheric, right? 1 atmospheric, and then pressure range should be like 1 atmospheric. And then you have the how many points and then the names of this. So if you go for here, and then if you select this, and then it goes to this paper, year 82, and then dimethyl methanol, 0 to 180 degrees C, pressures to 6.7 megapascal. So right, so in this case we want to have like, this is like a constant temperature. We want to have like an varying pressure. We want to see the constant pressure and varying pressure, varying temperature. So temperature range. So we need to see temp pressure, which is constant, and then temperature is varying. Say for example, in this case it varies, right? So let's see what happens here. This is 18 binary VLE, 18 binary VLE, but not isothermal, but this one. So this is pressure is not constant. This pressure is also not constant. Yeah, that's so easy, right? Yeah, so there's, I mean, we cannot, a minute, if we can do, for example, PXY. Temperature is, say for example, we use this one, 413 Kelvin. So how much is that 413 Kelvin? 413 Kelvin is 140 degrees C. So 140 degrees C. Oh, we can use this. 413. Right. So now this one. This is DME. And then we can then plot this. You compare, save data, save this data. save this data. So this one only, right? Because we want to just simply compare this. Save both data in the sensitivity, I'll say, and then yeah, fine. Click, we'll save. Click OK, and then here, and then for data that we save, and then we can see plot xy plot. Say now here. So this is the data that we save, and then this is the data that we predict, right? I mean, this is the data from the PSRK. This is the data that we save. So we can compare. I think we can merge plots and compare this plot with this data. See now, you can see. So I put now how to change this here. I want to have like a same y-axis. What? Oh, let's see. Y-axis map. Single y-axis, yeah. Okay. Oh, different units. We have a different units. Different unit. 1 minute. Texture. Remove this. This is in the. Why don't I do this before? This is from bar. This also need to be in bar. Oh, it's not really correct. It doesn't change the number. If I do this in bar, in pressure. Nah. Yeah, well, you can either do this in Excel or do it here. I don't know how to change the unit if you do this. If I merge this, because one is then using this, the other one is using that, so you can then yeah, to save some time, yeah. So you can copy this data, copy the data over here, results. So copy this data, and then copy this data in Excel, and then make the plots, and make sure that you have the same unit. Make sure that you have the same unit, so that the unit, especially in the y-axis, because it's they are close, but this one is over here, and then the other one is over there. So I need to make sure that this guy is there. So it could be like if we see this. Because the dots are the ones that using Newton per square meters. So if we reduce this guy down to here, to the line, you may see that this guy is then the lower, yeah, and then this one is also lower. So this one is also lower. But then you can see all in all, hopefully the this one's also like lower. So hopefully they match. The PSRK can predict the experimental data relatively okay. Yeah. Is this clear or no? At least this is one way that I can think of to evaluate. I mean, to compare the VLE predicted by the thermodynamic model that we have selected against the actual data. We can use this NIST database or the KIMA. I'm not really sure if we can see if we can then sometimes we need to have access, right? So sometimes we need to have access to the we need to pay. In this case, for sure, we'll have to pay. See, 90 euros. So we don't have the money to pay. NIST is free. NIST is free. The KMA is not free. This one design. This is also the Dortmund. This is the same Dortmund data bank guy. This is also something that you have to pay. Yeah. Nonetheless, this is an example how we can use NIST database to compare the predicted thermodynamic. To compare the results of the predicted thermodynamic model that we have selected. So we are now here, and then we can go to the simulation.
Doctor?
Yeah.
If we can we just use the proposed binary interaction instead of we change like we did before?
You can.
Is there any changes if we change the binary interaction in the simulation?
Of course they will change. If you change the number, like for example in this case, which is this BWRKT, something that I don't know. It's binary interaction parameter, but I'm not sure is this used by the PSRK or not. This is something that I don't know. Sometimes we have to PSRK. Because if we change the binary parameter, if you look at this NRTLF, for example, yeah, because this is easier, we have seen the data. So if we change the data, so it has the data on A, B, C, D, E, F, right? So if we change the data over here, it will then change the tau value, it will then change the G, it will then change the activity coefficients. It will also then change the how much is then going to the vapor, how much is going to the liquid, then what goes to the vapor and what goes to the liquid. It will change it. Yeah, it will change. So if we don't have any correct or accurate binary interaction parameter, we can for academic purposes, we can simply rely on the data bank that they have already. So this data bank. Okay, we can simply rely on this and then use it. And then the only, the one that I just showed you is simply to check whether those selected data banks in the PSRK how far or how close are they compared to the experimental data? So the experimental data are in the dots over here, and then the lines are the predicted ones. So if they are like this, for example, it's relatively okay, and then we can simply accept the default value. What is this status? Yeah, okay. Anyhow, is that clear?
Yeah, doctor.
Yeah. And if you can play around, yeah, you can play around. We can go to the simulations. Now we have selected the components. We have selected we convince ourselves that this PSRK is okay based on the short exercise that we just did. But please bear in mind, yeah, this is only like a predicting the vapor liquid equilibrium, because there are many instances. Well, there's few instances that I've encountered that the VLE is correct, but then the transport properties were not correct. So the transport properties in this case means the viscosity and density. So if the viscosity and densities are not correct, it's also not, it's not a complete correct thermodynamic model. And also what we've seen before, the thermal properties were not correct. So the reboiler duty, because the reboiler duty is based on the mass that you want to evaporate. Yeah, so it means the mass multiplied by the evaporation, the heat of evaporation. So the VLE for that system is correct. Because we tweak the binary interaction parameters in such a way that it matches the data. But then the reboiler was not correct. So the size of the reboiler at the time was like 3 times bigger or 3 times smaller. I don't remember. So because of that situation, how do we know if it's 3 times bigger or smaller? Because we have had another plant. We have had another plant at the different locations, about different size and a different process. But then that plant, that reboiler, for example, that distillation columns, it works almost similar. So it separates similar components, but then the reboiler calculated from the new thermodynamic model is different than the one that we have in existence. So that creates the discussion at the time. So please be careful on all of these thermodynamic properties, the vapor liquid equilibrium, the transport properties, and then the thermal properties. Thermal properties in this case is then your CP, your K, and then the heat of evaporation, heat of melt. Heat of evaporation is also the most important one. Okay, simulation analysis.
Doctor?
Yeah.
Doctor, I have a question. Let's say we already finish, do the simulation, for the whole system. And then in future, let's say we want to compare with different fruit package, for example, with different special mixing rules and everything. So is it okay? Is it preferable to do that way? To compare between different thermodynamic package.
We compare different thermodynamic package before we do the simulation, before we complete with the flow sheet typically.
I see.
Because that is then the basis. If that is not if this exercise, if we haven't done this exercise, the one that we just did like this, what was that? It's gone.
The comparison.
This if we haven't done this, and then we cannot convince ourselves that the model is correct, and then we cannot. I suggest that we don't move forward.
Okay, all right.
Right, because if we move forward and then we don't know, and then we have to go back and we change the thermodynamic model, and if we come back here, it may or may not converge, and then if it's big enough already, and then we don't know where to debug.
Yeah, understand that.
Right, so that's just simply
is it
because
preferably that we compare the VLE for each of the component involved, or just for the main component?
It's just for the main components. Things that we if we see well, ideally for all components, but it's not practical to do. Simply, for example, if we have for example, remember that the case that I have this dissolution columns, and then we see that this is like what 60% of the cost, for example. Right, 60% of the cost. 60% of the cost. And then since this is significant, and then we are not really sure whether, because this is like a B, C to separate, right? And then we're going to have C, and then we have A and B below, and then we know that B is lighter than A, for example. I don't know. So in this case, we better look into this cost comes from the reboiler because of the difficult separation, and that the difficult separations, we can then look into details. How is this B and C interacted, right? And also C and A. If we have the, I think it's also better because A is then closer to B. So if we can then see the data, and then we can then compare that VLE of C and B and C and A. And then they are okay, and then it's fine. If they're not okay, and then something that we have to modify, and then check again whether this is acceptable or not. But if this is like a 10% or 5%, it's so we don't really care. So but it's like if it's a big amount of money, that is something that we have to and then we are not sure. Yeah, we are not sure. And then it's something that we have to dig deeper.
Okay, thank you, Doctor.
Yeah. So how's the process looks like now? What do? We have 6 components, and then what do we want to do? So we have what do we mix first? So the way it's different, yeah. Okay. Now I have to mention, because this is important. Before we go, just please make sure that you get the data before we go there. The Aspen, it works like once we get the flow sheet, I will show you. But then just to give you a head start, so it works by default what they call like sequential modular OSM. So what it means is that it treats the unit operation as a calculation block, as a block. So say, for example, pump, right? So this pump. And then we know the equations for the pump, right? So the equation for the pump is then the energy is then what was it again? The mass, and then the volume delta P, right? The volume, and then multiplied with the delta P, right? This is the energy, and divided by the efficiency. Yeah, right. That's then the energy. And then how this works, that we have to then key in the stream. The stream has to be key in. So we need to fulfill the flow rate. We need to know the pressure. We need to know the temperature. We need to know the compositions, because these three specifying this three will then tell us the call it the phase of the phase of the the phase of the stream, the fluid, yeah, whether it is a phase gas, the gas phase or liquid phase, and then the flow rate will then tell you how much is then coming in. So this number, so we specify the input, specify input stream, and then in this block we specify input to the block. So once we connect them, so we have that flow rate over here, and then we know that this flow rate is the same flow rate as that one here, right? So this is a flow rate in volumetric, and then if it's in mass, and then it will then, once we know the compositions, pressure, temperature, and then it knows what is then the density, and then it can then calculate for you the flow rate. So it's strongly related. We know what the pressure in, right? But we don't know what the delta P. So that means before we can do the calculations, we either have to input P out or delta P. Or I don't know if it has like a pressure ratio, but this two is something that very straightforward. So if we input to the block the P out, it will then calculate the delta P, and this whole thing will then be in here. And then we also need to input the density, the efficiency. So this is input to the block. This is also input to the block. So if we specify this, specify that, and then specify the inlet stream into, and then it will then behind the scene, it will then calculate how much is then the V. We click run, and then we know, yeah, we have once we have specified this, and this can be calculated, right? So if we click run, and then Aspen will then calculate the W for us. Is that clear? And then it will then tell us what is then the next, the F is then the same. Pressure will be different, temperature will also be different, and then compositions will be the same, right? This will be calculated. Okay, so we have input, and then we have output calculated. Yeah, we click run. And then say, for example, this goes to like a heat exchanger, right? So this heat exchanger, we know that heat exchanger has this Q equals to mCp delta T, right? And then the M we know, right? So this guy will be in here. We know what the composition is, we know what the temperature is, and then the pressure is, and then they will then tell us what is then the CP, right? And then, so all these input streams have been defined, but we need to specify still the input to the block. So input to the block is based on these equations, and then we need to specify either temperature out or delta T or Q as well, so we can do so. So this guy will then calculate here, and then this will be calculated. This can be calculated, and then we click run. It will then calculate Q. Once we calculate Q, and then it will then calculate for us the output streams as well. So this is an output calculated. P, T, Z. So this is another block of heat exchanger. And then so on and so forth. So it goes by block, by block, by block, and so on and so forth. So this is block they call module. So 1 module, 2 module, 3 module, and so on and so forth. So it's like a modular base. And then the calculation goes sequentially, hence the name sequential modular. Yeah, sequential modular. So we cannot, for example, in this case, we cannot make the whole system without running one block. It's not advisable to do so. So we just have to start from scratch. We start from one block and another block and another block, so that we are sure everything is then being calculated and converged nicely. And then how does it handle recycle? Because recycle means something if you have something, and then it goes to another block, right? And then there's another recycle, and then blah, 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 blah. So we know for sure, based on this understanding, this guy will not be able to calculate it until we define the inlet stream, yeah? Yes. And this inlet stream cannot be defined if we don't know what's in here and what's in there. This one we know for sure, we know because we specify it. But this one, how much is this? This is something we don't know. Hence, Aspen, in this Aspen Plus, later on I will show you. It will then define this as a test stream. So it will then say this as a test stream. It will then assume this. Or we have to assume this. Yeah, either we or Aspen. I will show you how and why. So we assume this, and then it will then put it over here, and then this one will be calculated. This will be calculated, and so on and so forth. So first, until this one, it is calculated. This is calculated, and then this guy will then come back over here, and then it will then calculate it. It will then compare the delta. If the delta is then low enough or small enough, and then this whole thing is converged. If this is not, if the difference is quite big, so that means it will do modifications of this number. Either it just goes straight or modified depending on the method for this recycling. I will show you where this is. And then it will then calculate the new assumption and then restart the whole cycle again. Yeah. So you can imagine if we have many recycle, or somewhere here, somewhere there, it's going to be a lot of how do you call it here? A lot of iterations, and it may take some time, and it may or may not converge. It may or may not converge. So that is then the sequential modeler. But having, I mean, to be able to go through this, to use these calculations, as I mentioned over here, you can imagine that you will need a stronger process engineering knowledge, because you will need to know what is then required by the pump, what is then required by the exchanges, distillation columns, reactors, and so on and so forth, before you are sure that you can run this. Right? I don't know, I might make myself clear. So it's in that way, it is not that user friendly compared to the other solver, but then for sure, if you can run this, you gain a little bit more confidence in your understanding of process engineering. So that one I can assure you, I can guarantee you for that. Any questions on this? Otherwise, we can then quickly go. So
Doctor, sorry,
yeah.
I have a question. Okay,
Yes,
let's say what about if we perform for the matter energy balance? I mean for the complete system manually, meaning to say we get all
Yeah.
the unit
Yeah.
operation together with all
Yeah.
the required streams,
Yeah.
stream composition and everything. Then we simulate that. Is it okay, or straight away use the because from that we can at least avoid the hassle of recycling?
Yeah, I mean, that's also even, yeah, I mean, that depends on how you solve the recycle in Excel, but nonetheless, assuming that is done correctly, that is in fact the, how do you call it, yeah, the most favorable way to learn, yeah, from the from the student's perspective. And then because then if we can do the calculations correctly in Excel, and then we can then prove it that we have done, I mean, if you can prove that the results are the same or quite comparable with the process simulation software, that means you will then boost our confidence. That's number one, and then we are sure that we understand it correctly, right? So that's the I think the main benefit. In the past, because chemical plants, it's not as easy as to model as this refinery or petrochemicals, simply because we are dealing with a strange thermodynamic situation. Most of them, yeah, those plants, they were done or designed or science in Excel.
First.
So I think I've involved in 7 plants. So 1, 2, 1, 2. Only 2 we use Aspen Plus. The other 5 we use. See, 3 we use Aspen Plus. The other 4 we use Excel. So Excel is our mass and energy balance process simulation. So it's just very, and then those plants are standing still, so it should be okay. Yeah, I would encourage. I mean, for the students, I would encourage them to start from Excel. So simply to understand, I mean, simply to put these equations in the back of their heads, right? Right, and then yeah, distillation column is quite difficult, but then if we know how Mercantil diagram works, that should be okay. And then reactions, we need to understand the kinetics and so on and so forth, how they are connected and how the equation looks like. It's really beneficial, I would say.
Okay.
So, very good. So what do we do? What do we mix? So we have one stream. So we just like here we have and on the below, yeah, in the below, it's not on the left. So in the below we have blocks that we can how do you call it? We can use. Just simply like click 2 times. Batch model, user model, hierarchy, user model. Yeah, I don't know. Maybe this one can be used. Yeah, we'll see. This one. Photon. So if you can then make the equations in here, and then you can see. So we'll see. We can do something. Yeah, mixer separator. So materials. So we have, what do we have? We can just sorry, I forget. So we click this. We have also like drop down. So we have material, heat, and then work. So yeah, this one, heat and work. We can do it later. So material stream. We click on material once, and then you see your circle becomes something like this, and then you click it once, or you can just double click it, and then it looks like this, and then click another one like that, or we can click once and then click something. So click twice, so it's so many click. We click here once, we click the source, and then we click the sink. So 3 clicks. You can see, yeah. So that's kind of how we put streams in Aspen Plus. And then here we can rename it, but I think it's limited by 7 or 8 characters. I don't remember if you would like S. So no. So 1, 2, 3, 4, 5, 6, 7, 8, only 8 characters. So we have to be very neat in our naming. So what do you want to now have? What kind of stream?
CO2 and hydrogen.
Hydrogen, yeah. Hydrogen. And then?
Doctor, before I have question. Before we started the simulation, may I know if we have to insert all the required operating to simulate the in Aspen Plus because in Aspen HiSys we can simulate the each equipment.
Yeah, you can. You have to
One
even
by one.
like I mentioned, yeah, you have to key in one block and in one stream, run it, and then you get the result over here. You get the results here, and then you add another block, and then you get the results over here, and then you get another block, and so on. So it's building up. So it's advisable. I mean, it's common practice to start. I mean, to model this from one step at a time, not the whole.
Actually, I have simulated the process in Aspen Plus, but if I didn't insert all the required operating condition up to distillation column, I cannot simulate the process. I need to
because
fill up all.
you must miss somewhere. That's why this when you say that you have flow sheet, that means you have when you add one block, do you run it and then you get this stream or no?
Oh.
Right? We add one block and then we run it and then we get this stream, and then we add another block, we run it and then we get this stream out. See, we calculate this we input first step, we input this, we add this block, and then we input the parameters, and then we calculate that, and then this one will then be calculated, and then we add this block, and then we input the parameters, we run this, and then we'll get this stream, and so on and so forth. So you cannot put like stream and then attach this, attach that, attach this, and then you run. This will, and well, if it's straight line, it will work. But then if it's you have so many recycles, it will not work.
I see. Oh, okay.
Yeah. So let's see how big is your simulation. I think we can do so. I mean, so this goes through this. So if you can open your simulation and then let's walk through. I mean, you help me. So this hydrogen line. So what's in it? So you double click, and then and I assume it's only like hydrogen, right? So the mass or mole fraction is then 1. And then what is then the temperature?
25 degrees.
25. And then the pressure?
1 bar.
10 bar. Mole or mass flow?
1 bar.
Or 1 bar. And then flow rate?
6.8
Mole or
kilomole per
mass?
hour.
Huh?
Kilomole per hour. 6.8.
6.8. Very strange number. I don't know why.
Actually, this is a pilot scale operating condition.
Fine. Okay. Okay. So it doesn't matter. So you can see it's blue. Means it's blue. It's okay. So this stream is complete, and then you can is not complete. Yeah. So stream hydrogen is complete, blue, and then stream 2 and stream 3 over here it's not complete. So so do we have any other stream as to get the first block?
Yes, CO2.
CO2. And then you double click, and then pure CO2. Is it pure CO2?
20 point.
Is it pure CO2 or no?
Yes, pure CO2.
And then pressure, temperature?
25 degrees C and 1 bar.
1 bar as well. And then mass, mole?
20.4.
20.4 kilomole per hour. Yeah.
Yes.
Okay. And then do you have any other stream?
No.
No.
It's
Okay,
only
just delete that. So in this case, it's not complete. We need to have a block, yeah. We need to have a block. It says not complete. We need to have a block of. So what do we do with this? All at the ambient and then the atmospheric pressure. So do we want to compress it, or do we want to mix it and then compress it, or what do you want?
Mix it and compress it.
So we mix it, yeah. So mix it means it's one block already. So if you go here, just click it and then click there. By the way, you can change this to a different thingy, yeah. And so I think you can then rotate icon, exchange icon as well. So this one double click, and then you can then click it over there, and then or from here, or we cannot do so. So we can simply double click and then connect, or right click and then reconnect destination, which is there. So, and then from here, we connect the material in here, product, right? Okay. And we have S4, and then it says this required input complete simply because it has a default parameters. There is no pressure drop, and then mixing like vapor liquids, so both vapor and liquid are mixed, and there's nothing else to be added. Yeah. So and then we so it doesn't have the option of either it is using the lowest pressure or equal pressure or whatnot. It has nothing there. Just specify the pressure drop, and then in here you can click run. So the way you click run is you click this one, next input, and then it will say run simulation now or no. Click cancel. I want to show you something. So you can click this control panel, and then you can then clear message for now. Yeah. So if you click step first, so it means it just step one block at a time. See, if you click step, so it will then process the inputs and then analyze the process. Okay, this is from the property stuff, so we can just remove that one later. So we'll remove this. This one deletes. Okay. Now, where was I? As well. And then I will then reset simulation to show, and then step. Nah, so once we click step, so it is one step. So it will then say, it will then analyze the flow sheet. So the computation order for the flow sheet, remember that one? So the order is that this order. So which block does it want to solve? So it moved from one block to the other block, and then it says that we have only like one block, right? B1, which is the mixer. So B1, the model itself is the mixer. So it's just like one step, and then the simulation is completed. So if we do so, that means we have already the results over here, and then that S4 becomes like a blue, and then we can see the results is there. Yeah. Before, I will show you now. If I delete this, I put that stream. See, that stream 5 looks like this. So it doesn't have any results. Doesn't have any results. So we have the input, we have the inputs, we have the block. Well, we don't put anything in the block for this specific mixer, but then it's there. So we have input, we have the block, and then we don't have the output. So we click like run, and then you will then see the results is there. See. So now we have the results, and then so once we mixed it, we need to add another block, right? What do we do now here? Compress it. So pressure changes, and then we go to the compressor and then put it over there, and then double click, and then we have to put it there, and then put a stream like that. And then this one is calculated already. And this block, we haven't done anything. So we have to go into it, and then we'll have to specify it, because block is, this compressor it needs a certain value, right? So it works something like this guy, pump. Yeah. So it's we use compressor, and then it's isentropic. So there are plenty of models that you can use. So we can just simply use isentropic or polytropic. I don't know. Just use for isentropic for the time being. And then so we can then specify discharge pressure, pressure increase, pressure ratio, or power, or even the performance curve. So in this case, I assume that you specifying the discharge pressure, right? Or no?
Yes, 40 bar.
20.
40.
Or 40. Now here you can specify the efficiency. If not, then default is 1. This one as well. The default is 1. No, default is 0.72. See, 0.72. Otherwise, then if you don't specify anything, it will be the 0.72. If it's if we specify it to something, and it will be using that something. So we have 2 inputs, right? Like I mentioned over here. So the pressure and then the efficiency. So the efficiency, we have the numbers from the default. I'll let it be if you want to. And then you can see if I use one step again. Now, see, it calculate B1 and it calculate B2. B2 is then the compressor. It doesn't calculate B1 again because B1 has been calculated. This has been calculated. We have this calculated already, and then it's just a matter of this guy. But it shows us, well, if I were to start this from scratch, I would calculate B1 and then B2, right? So it's completed, and then it's completed, and then you have the S6 as the input. Okay, now we can move on. Now I think it's clear, yeah, how Aspen calculates things, and then this is then what we call like sequential modeler. We can now proceed at a much faster rate. So what happens after we compress?
Sorry, is there any way that we can see the temperature or pressure values quickly without looking at the clicking into each of the material streams? Probably.
Yeah, we can. This one. We can have it. So I typically, very good, very good. I typically click this temperature, so you can see this. What is this? I don't know what this is. 497 degrees C, 25 degrees C, and then the pressure is then this guy. So 1 bar, 40 bar, and I typically also use mass flow rate. So this mass flow rate. So I always use these three. It's there. Now I just realized, yeah, this 497. So this one stage is not correct. Yeah? We are compressing it like a 40 times, so it's not correct. So we need to be well, to make a correct process assessment, we have to make it as practical as possible. So in this case, we typically limit this to like a maximum 150, 160 degrees C because of mechanical issue. So if we compress it and then we don't compress it to like a 40 times, so we I don't know, maybe 2 or 3 times, maybe 4 2 or 3 times. So for example, if I compress it to like I don't know, 3 for example, and then you can run it, and then you can see it's a 139. But if you could, for example, yeah, try to force it, and then 174. So this is too big already. So so 3 is okay.
We have to do multiple compression.
Yeah, we have to do multiple compression, and then here we cool it down. Where is that exchanger? It's heater, but it's a cool. You can use it as a cooler. It says heater, and then you do it this way, and then you send it to like a flash. Now we go very quick. And then remember that I don't specify here and there, but I put these two blocks together simply because they are like one sequence. So here we cool it down to like 60 degrees C. Pressure drop is I don't know, maybe you can put it 0 or you can put it minus. So if it's minus means it's pressure drop. It's 0. It's a see. So absolute, if we put a positive value, that means it's absolute unit outlet pressure. If it's negative, it's then the pressure drop. So if we take, for example, in this case, negative point, I don't know, 0.2, but so it's then the pressure drop, and then this guy is then the this is simply like separating the liquid if there is any, and then the vapor. So I would say we can use like adiabatic, yeah. So it's adiabatic, so there is no heat coming in and out, and then there is also no pressure drop, right? Because it's simply like a flashing it, if you want. And then we can then run it, and then you can get this. So 360 bar, 360 degrees C, 3 bar. And in this case, it's not 3 bar because it's 0.2, right? Minus. So we can go here, and then can pressure. Right? Pressure, we typically put 1 dimension, 1. Temperature is 0. Yeah, should be okay. So it's 2.8 because delta P is 0.2, and then there's no delta P over here. So 2.8, 2.8, and then we can see there's no liquid. But this is the typical the main process in one stage of compressor. I'm not sure if you can copy paste, but then you can. I don't know if you can copy paste. Yeah. Can you copy paste? Oh, we can. We can B2, B3, B4. Right? You copy paste. I'm not really sure. Yeah, there's a ID conflict, so we can well, you can explore that one. Yeah, but it's just like so here 3 bars, and then we can then where's that again? So pressure changes. We can compress it, change it, and then because why I do this simply because in the later on you will need this equipment for cost calculations. If otherwise, we can just simply how do I skip this? This one is no adiabatic, no pressure drop. This one is 60 degrees C still, and then another 0.2. This one is then put it there, and this is, if we then say asymptotic, and then discharge pressure is big 10 in this case. And this 208.10 is not okay. 9, it's also not okay. It's also not okay. This should be okay. Right, and then and you can imagine how the even though in practice you will see these stages in one building, but they are stages, so here you have like one stage, as if it's like one equipment, but then in reality it's simply like one big building of equipment, but these stages are in that particular equipment. So you can I don't know if you will need another stage. I think firstly you will need another stage. Pressure drop, adiabatic, and then also 60 degrees C. And then this one as well, isentropic. And then this is then 7 times 3 is about 20. 185 is 19. Yeah, okay. Yeah, okay, 170. And then we have another, so 1, 2, 3, 4 stages. Okay, amazing. Danger. I think we can, can copy that one. Right, so even the flash here, if you compare with the other process simulations, the default values are used, right? Adiabatic and then no pressure drop. So we don't have to specify the flash, but in this case, Aspen, we have to specify. So that's why it takes more effort. But then when you do this, it's you know that these are the degree of freedom that you have to specify, and then by doing this, you know that what needs to be done for each of the units. 40. Yeah. So now you have your 40. Make it 41. 40.2. 40. Right. So you know. There, you have 40 bar of gas. See, press home and you will see the entire stream. But you could also use like a hierarchy, and then you block this. I don't know if we can do this.
Sorry. May I know how did we know whether the temperature of the compressor is suitable or not to proceed with other stages?
You don't know from this one. It's based on your practical knowledge.
So let's say for the second stages of compressor, just now first you put 10 bar and the temperature increase, the temperature difference between the first compressor and second compressor is quite high.
Oh, no. You have to look into the outlet temperature of the compressor. So here, it's 139 degrees C. So this outlet temperature is then the highest temperature in the compressor, right? So we need to make sure that this number, this temperature, outlet temperature, is lower than 150, 160 degrees C. Somewhere around that. So this one is somewhere around that, Yeah, I mean that's why I try to manually adjust the compression ratio or the pressure outlet in such a way that this temperature is at maximum is 170 degrees C.
Maximum is 17.
Yeah, in
Degrees
this.
So the temperature for the compressor need below 170.
Yeah,
170.
below. Yeah, to be on the safe side. Yeah.
Yeah.
That is practical knowledge. I think you can, if you Google this, I mean, there is also someone must have written that this particle number in one of the textbooks. And indeed, using one stage of compressor is the common mistake that undergraduate students use. So I see that more and more, but and then this is then how I told them the correct way to do it. So then they know why we have because in the compressor house, typically if you go to a compressor house, that compressor is very long. That compressor is very long, and then you have cooler going in and out, and then you wonder. I mean, in my book, we have only like one thing like this. There's no such thing as cooler. There's no such thing as a separator. But in reality, you will have cooler, separator, compressor, next stage, cooler, separator, next stage, cooler, separator, next stage, cooler, separator. So these three items are there. Okay, I don't forget to say. Don't forget to save. And then now, once we compress it, what do we do?
Sorry.
So what do we do with this gas, compressed gas?
We heat until it reach 240 degrees C before entering the reactor.
240 degrees C. So you have the exchanger. Stream. For the stream first, yeah. Otherwise, we cannot calculate that one. 240 degrees C. Your reactor is how much is that the specified pressure? 40.
Sorry.
What's then the required pressure of your reactor?
Required pressure is it the range of the reactor?
Yeah, what do you need? At which pressure
40
do
bar.
you? 40 bar.
40 bar. Yeah.
So that means I have to increase this to 4.4. I mean, I'm being very yeah. So you have 40 bar at the inlet of the reactor, you say, and then you have your reactor. Yeah.
Then enter the reactor.
And then the reactor information. What kind of information do you have for that reactions?
Kinetic equation.
Yeah, the kinetics equations. Okay. So in this case, we can use. I think we can use PFR.
R-flux.
What do you use?
R-flux.
Which are?
This one R-flux.
Plug and flow. Plug and flow. Plug flow reactor. So yeah. you can use this one, which is nicer. And then yeah. So reactor type is I'm assuming it's adiabatic, no?
Yes, adiabatic.
So adiabatic, right? So yeah, in the other software they don't have this kind of options. So those options are like something that you have to think about. But in this case, it has these options. So adiabatic reactor, and then the configuration is that it's like a multi-tube reactor. Or it's like a one reactor, one tube. I don't know.
I think from literature review, they use one tube.
One tube. And then the length of the reactor is?
Since the literature review is only in a pilot scale, so I just use the length is 2 inch.
2 inch, okay. Okay, so when we and this for the I mean for the first trial, yeah, later on you can modify. So what I want to say later on, if we when we do techno-economic analysis, no matter what the scale that we have currently at the lab or where we are in the whole chain, because I mean, so we have in terms of technology progressions, we have the lab, right? So we have a conceptual idea, and then we have this like a lab scale, and then like a pilot scale, and then we have some other scales, and we have commercial scales, right? And then typically we have like the same like this in that compressor ratio. We cannot jump from conceptual to commercial scale or lab scale to commercial scales. So there are some ratios, some size ratio, capacity 2 divided by capacity 1. So there is this ratio which is different from technology to technology, from region to region, from experience to experience. But this is something that we have to obey. So if we do techno-economic analysis, it has to be always in commercial scales. Yeah. So even though that we have like this, maybe then the 1 gram per second. So your commercial scales is about like a 100 or 10 kTA. So this techno-economic analysis has to be done on 110 kTA. Not this one. This is no, but this one is yes. Yeah. So and then if you scale down, so the reactor will also be like a 110 kTA. So if you have like a membrane, you don't find any 10 kTA membrane, so that means this 10 kTA is about, for example, I don't know, so 10 kTA divided by 8,000, make it an hour, and then then 10 times 1,000, so make it in ton. So here, so it's about 1 ton per hour. That's about 1 ton per hour. And then your membrane says, well, my membrane is not 1 ton per hour. My membrane is like maybe 20 kilogram per hour. So that means you will have like how much this is then? 50 membrane reactors or membrane tubes, with tubes. Yeah. So this is something that you have to do later on. But then this is just for the sake of effect yeah, this introduction of simulation, we can do so. So the length is how much is it again?
2 inch.
2 inch in length.
2 inch.
And then the diameter.
1.5
inch.
Yes.
Okay, fine. And then the reactions. Now, here we need to, I think we need to specify the reaction somewhere here. In this case, so right, so we click new and then reactions, and then you say you have the kinetics. Let's see which one is then.
Power law.
Power law, yeah. Okay, power law, and input complete. Yeah, this is the input, and then click another new reaction 1, and then which reaction is this now?
CO2.
CO2, and then
Plus hydrogen.
Hydrogen for the reactants. That's it.
Yes.
And then okay, how much is then the CO2? Oh, sorry, products first.
Methanol and water.
Methanol and water. Okay, so how much is then the CO2? How many mole?
One mole.
So -1, and hydrogen?
3, negative.
This is 1 and 1, yeah. Yeah, or no?
Yes.
That's right. And it's kinetic, yeah. And then click next.
Doctor, may I know, as for the exponent, what should we put there? Exponent.
Which exponent?
At the, yes, exponent.
Ah, very good. So this sorry. Okay. So your kinetic is something like this, right? So when we used to like R over A, and then minus K, and then CA, and then CB, for example. And then this is exponents 1 and then 1. So if it's 1, 1, that's 1, 1. If it's like 2, and it's 1, and then it's 2 and 1. So if CB is not there, so if it's minus K, CA, 2, and then CB is not there, that means CB is then equal to 0. So this is the exponent. So the exponent of this, because this is then the kinetics information. Okay. Okay or no?
Okay, doctor.
Yeah. So now, since you I missed it, so thank you very much. So your equation, how does it look like? So is it something like this? Something like this, yeah, I hope.
I think it's 1 exponent.
1 for CO2 and 1 for hydrogen.
Yes.
Oh, okay. This one is something that you have to make sure, yeah. Because now I'm just assuming that you're all this is then 0. Oh, it's default. I think it's 0. No. You could also see the see if not entered reaction rate, it does not depend on the component. So that means it's 0. And then you can then see how, and then click next, and then your kinetic information, and then this is then the K. So reacting phase is then the vapor, I would say, right? And then the rate base is the volume or catalyst. So this is something that you need to define, is it based on the volume or catalyst. Now assuming, I don't know, yeah, now it seems that we assume it's based on the, I mean, the volume of the reactor is then the volume of the catalyst. That's what I'm now assuming. Is that, am I right to assume so? I mean the now is then the fixed bed catalyst is more like for example in this case this is then your bed of catalyst, and then you have that something like this, like this, and then you have the volume, right? And in the from this length, and then this D, you get the volume, of the whole thing, and then you have like a void fractions, right? Void fractions. And then from this void fractions, you have void fraction something, I don't remember, void fraction something like this, void fractions. I don't know what the symbol is, but then from here you can then calculate the actual volume of the reactor, the actual volume of the catalyst, if you know this void fractions, right? Is that, for example, that your void fraction is then the 70% or 40% or whatnot, and then this then the, say for example, this then the 30%. So volume is then volume reactor divided by 30%. And then if you know the density of the catalyst, and you can calculate the mass of the catalyst. Yeah. Now that's what I assume. That's why I leave it here. Correct me if I'm wrong. Now, go on.
Actually, I'm not sure for the rate basis whether we use the reactor or catalyst.
Say it again. Moderate basis.
I didn't know whether to use the reactor or catalyst for the rate basis.
Either way, you can find. I mean, as long as you understand, weight basis means the volume will be. I mean, this will be then based on, because this is then mole per volume, yeah. This one, the C, mole per volume, right? And then this then the volume of reactions phase. If it's like a liquid, and then the whole liquid reaction, the whole liquid as the reaction phase. If we have like a hollow like this, a reactor like this, and this volume is then the volume of the reaction phase. But if we say, well, this part is then the mass, you can say, well, the mass of the catalyst, or the catalyst is then where the reaction phase. So that means this concentration will then be mole divided by the surface of the catalyst, or the mass of the catalyst. You can safely say so. You can safely approximate it that way, because it's impossible for us to calculate the surface of the catalyst. We simply we simply plug in. Okay, so we have this volume of reactor typically, and we can just put in like 1 tons of catalyst, and then this 1 tons of catalyst, we don't really care how much then the surface active of the catalyst. We just simply like 1 tons, and then with these typical void fractions, we know what is then the outcome. So in that sense, we have this this concentration becomes the mole divided by the mass of the catalyst. So either way, if you do it this way, and then you can then end up with the mass catalyst, because this mass catalyst is then going to be used for your economic calculation later on. All of this mass catalyst is going to be done in the economic calculations. So it really depends on which versions do you want to approach it. It's just that we need to make sure that you know and you understand why you pick one over the other. Okay, so here I showed you that this volume, how the volume is then connected to the mass. Yeah, how the volume is then connected to the mass. So if you know mass, and then you can then walk backward to calculate the volume, or you because then in this case, this guy, this L over D, you need this to calculate the material cost, right? Yeah, so either way, if you specify this volume, you know this first, and then you know that one. Or if you specify the catalyst, that means you know this one, and then you will have to calculate backwards to know that number. So either way, you need to have this dollar and then that dollar. It doesn't really matter where you start, from here or from there. It's all up to you.
Doctor, I have a question. Like usually we will compare with the experimental result, right?
Yeah.
Normally for experiment, we will use like powder, and we will dilute it with like inert thing like silica carbide and so on. But when we do like simulation, it's for a big scale. So the catalyst that normally people will use at industry will be in pellet form. So will it be like any different later on when we want to compare with experimental and also the one that in the simulation?
No,
Based on your essay.
Yeah. Yeah, I mean that's it is true. I think what you yeah, in the lab they have something like this, right? In the lab there's something like
normally
this.
we use powder, right? So
I know.
we don't like
So you have this your powder, right? And you have this like inert, and you have this inert, and then there's another, I don't know, some other stuff, and then this inert is simply like a sponge or whatnot. Anyhow, so this is then basically, this is then your active site, right?
Yes.
This is then your catalyst basically. So the volume or the mass is then the volume of the catalyst of the reactor, sorry, volume of the reactor, and then the mass of the catalyst. So this one is then what we just discussed. All of this is this guy.
So we eliminate the let's say they have two sections, so you just add like the two section, but we eliminate the inert In the
Yeah.
oh, okay, thank you.
Yeah. Typically, we have this inert or support, and then this why they separate these two. I mean, in the lab, I mean, if in the lab, these two must have like a slightly different function or different functions. But then in the real world, this is really like a support, because there will be like a channeling, right? I mean, because this guy, the way this reactor is going to be put in, they open this. There's another guy over here, right? And there's a crane, and there's this big box of catalyst. They just dump it, and then depending on how they dump it, and then it's also like they have to be very careful, yeah, otherwise it will then create static electricity. So the void fractions will always be different from one overhaul to the other overhaul, and then when they dump it, there will be like an attrition of the catalyst. So it's not really clear how the catalyst is then uniformly distributed or not. So for sure, it will then create like a channeling. I mean, the easiest path for liquid to flow or the gas to flow. So this is something that we want to minimize. So that's why we have this kind of stages. So we know, I think there's a rule of thumb between the L and D. For a certain diameter, we can go as much as to a certain length. I have to look it up what this value is, so that for example, this one we need to have like maybe 2 stages, and then empty, and then another stages, something like this. So this is simply to minimize the chance of a channeling to occur, so that we can have like a very nice and uniformly distributed flow of fluids, which is perfectly resembles the lab versions that we have, coincidentally. But yeah, I just like well, it's a nice thing to see. But it's clear, yeah. So it doesn't really matter. I mean, whether we start from the volume, we will end up also with the catalyst, the mass of the catalyst, or we start from the catalyst and then we will then also end up with the volume of the reactor, because we need the cost for both. We need the cost for both things. And this part is then what basically the active part of the catalyst. So and then when we size the reactor, and then we simply then have to account. For example, we know the volume of this one, but then for the size of the reactor, we will need, for example, some meters more. Or so it's something that we have to take into account, you know. And so it's not like if this then the like one cubic meter and then the whole reactor will be 1 cubic meter. It's not that way. So we have to account for the empty space over here and over there, and so on and so forth. So but it's easy. I mean, it's just like a matter of multiplying it with a constant factor. Okay, now the K. How much is then the K? So this one, yeah, if we have like a reference, I'm not really sure if we have reference, but if not, then we can use this KT, and then this is then the Arrhenius constant. Do you have this? Okay.
Yes.
Okay. How much is that?
1.09.
1.09. This t to the power of n, do you have it, or there is no t? There's no t.
Don't have.
Okay, fine. And then the activation energy, the exponential factor, activation energy.
87500.
87500. And the unit is?
Mole per kg per mole.
Kg per mole. Kg per mole. There's no T. Okay. So based in molarity or partial pressure?
I think it's a partial pressure.
Okay. Yeah. And then the activity now. Right. So any other reactions?
Actually, we have 4 reactions.
Okay, let's do them all. Or you want to do it on what else?
CO,
Mm-hmm.
CO plus hydrogen.
Mm-hmm. How much it is?
CO 1 and hydrogen 2.
And then this one, one in
And
one.
yes, only one.
And the product.
And the product is methanol.
So no. And then this is 0, yeah. Any other reactions? 4, yeah. And then what
Yes.
else?
Methanol.
Methanol and
Methanol, only methanol for the reactant. And the product is dimethyl ether and water.
okay. This is 2, yeah.
Yeah. 1.
And then another one.
And the last one is carbon dioxide plus hydrogen.
Minus 1. Okay. And then product is?
And the product is carbon monoxide and water.
Okay, very good. So now, this one vapor, partial pressure, K is for second one.
4.89 exponent 2.
Exponent 2, which is 489, and then E?
113 000
0, 0.
0
That's it.
30
Oh, 30. Okay. And kilojoule per mole. And then the the third reaction. Okay, is
1.8473 exponent minus 10.
minus 20.
Minus 10.
Minus 10. Oh, it's very small. I mean, this doesn't happen anyhow. So, okay. You know that this is not going to happen, yeah? If I see the K of the other 2 reactions. And then the E?
4084.1.
408, 4.1, like this.
Yeah.
Okay. Okay, do you understand me? Yeah? I mean, this K is then the, because it's like weighted K, huh? So this K. So if the other K is like hundreds and tens, and then your reaction number 3K is only like 0.0001, for sure that's not going to happen. But nonetheless, therefore,
And the fourth one is 9.64 exponent 9.
say again?
9.64 exponent 9.
Oh, this one happens a lot. I mean,
Actually,
okay.
I get this question from literature review. I don't know whether is there any error at the -10.
Yeah, I mean, that's why we have to be, I mean, fine. This is just for the sake of getting this Aspen PLUS works. This number is very important because if you, because the other reactions, like, just complete this. How much is then the E?
152 900.
900.
152.
152. So see, this number is millions, and then this number is over the millions, and this number in the hundreds, this number is in the 1. So we have 4 reactions, each of them works at different scale. And then if we put this into the calculation, obviously, if you see reactor 3, reaction 4, so we have CO2 and hydrogen as the we have? What did we have the input? On close. So we have in the input, we have hydrogen and then CO2, hydrogen and then CO2, hydrogen and then CO2, hydrogen and then CO2. See? So this guy will happen, it will then create CO and it will create water. And then the rest, this one, it's one. It has to compute. It has to compute with this guy, which is no way it can compute. It can compete. Sorry, it can compete. So this is then your, it's going to be your predominant reaction, and then so you will make CO and water, and then your CO if there's any. So this one will then go if we have enough CO and then you have enough hydrogen, and then you will then create methanol. And then this is if you have lots of methanol, and then you will then be able to see these results, because this is very small. So you will need to have a huge number of methanol, then you will then see these reactions. Otherwise, it's a no. But nonetheless, so we have the reactions, right? And then so we have to say this. Now this is then B5 is react. And then this reaction sets. So you are okay. Pressure drop, I mean the specified pressure drop, and then pressure drop is then being specified as 0. Otherwise, if you can then use friction correlations, I will then use this. Say, for example, see, you can then use this ergon, for example, in this case, right? So you can use ergon. And this ergon, you will need to know the catalyst size. See, the catalyst size. And then you can click ignore, but you have to say catalyst present, and then you can then say this. But nonetheless, it's simply use. I don't know if you have the catalyst information. That one I don't know. If you have, then you can tell me. Otherwise, we can then use this number. There is no pressure drop, or you are sure that, well, we will then design this catalyst inside of the reactor with a specific pressure drop. So that's also okay. Yeah. So in any case, if you specify it this way, no, before I go, do you have any information on the catalyst? So that's one step at a time.
We don't.
We don't. Okay. So yeah, this is it, right? This one is if you have like your own pressure drop calculation, but this is then if you say pressure drop is 0 or pressure drop is something, you could also specify it to be something. Let's put like some realistic value. Okay, yeah, and then you can then click next. You can then click on simulation, or you can go to that control panel, right, and then click one step so that you can see computation order. You can see B1, B2, B3, and so on, so it works one by one. So step by step, block by block. You can see now here. So work from here to there to here to there to there. So there's no recycle, so it's also still good. So if there's no recycle, you can then simply plug in everything, all the numbers, and then run them all at once. So that's an option compared to what we just did, like one block at a time. But I'm just showing you the ideal pathway. Then you can then click what was it? Oh, completed already. So because it's only like one. Completed already, and then you can see not doing anything basically.
Doctor, in the first sheet, can we display the material stream so that probably we can have a quick look on the...
We can, but I don't remember how. We
Okay.
can. That one I know. Because once I asked I did this in the past. So we have like we have a material streams down here.
Like a stream table, right? Stream table.
Yeah, exactly. Stream table. So but I don't know how. I will let you know once I know how. Yeah, there should be somewhere.
It would be really helpful if, especially after reaction, we can see whether our reactions.
I know. That one I know. I perfectly understand that one. I also want to know that the results, stream results. Sorry, this one. Okay. So the pressure drop is it's not 0.3. Oh, pressure drop, not pressure. Okay. Oh, it's not doing anything. Yeah. Does it do anything in your version? Aina, right?
Yes, I didn't get any reaction here.
Oh, this is the one that you are stuck.
Yeah.
Yeah. So I think we need to be careful on the
Is it related to the kinetic equation?
Yes, it relates to kinetic. Because this is then the one that is then being the highest, reaction number 4. And reaction number 4 is this one, CO2 hydrogen. So it should give CO and water. Let's see, CO and water. This one, stoichiometry is. Did we 1 minute edit reactions? We have 1 and 1 points. Yeah. That is one. And then another one is that you have like 1 inch length of reactor, right? You can then see, where's my pen? Oh, see, this one. So the kinetic is then if you see dc dt, right? So it's a mu minus k, and then dc, let's say dc1, dc1, sorry, c1, then 1, and then c2, and then 1, right? And then this T is the change of concentrations of it's basically, so if we have like this is then the T, this is then the concentrations. It will then, if it's like this is second order basically. So if you look at first order, it will look something like this. And then this is then the concentration that we expect out. This is then C in, right? So after this time is 0 time. And then this is the time period, right? Time t. And this t is basically how much it takes to react. And then if we translate that to a reactor, right? So a certain diameter for your capacity, and then a certain length, and you have a flow rate, right? So it will then, if I put this graph into here, it will look something, if it is 100%, this then 0%, it will look something like this, something like that. So by the end of the reactor, your concentration will then be at as low as possible. But if you extend the reactor a bit further, and then it will then become like that 0. But then if our reactor is only like 1 inch, which is this, so there's nothing. So that's what I'm now suspecting. Because our reactor is 1 inch. So 1 inch or 2 inch. So if we say, yeah, say for example, where's my reactor? Reactor. Where's my reactor? This one. So if I say configuration, so it's 2 inch. So if I say like 2 meters, a meter. Now run. Results. Strange. This one is strange.
Would that be like because we don't like put the catalyst size?
No,
Is
no,
it
no,
like,
no, no,
no.
no, 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 no. No, that catalyst is on the is because of the pressure drop requirement.
Oh, okay.
So the whole calculations on the reactions are done in this kinetic model. Let's see. Yeah.
Like the number. Perhaps I know you might have like taken from different references which have different unit, or
Unit
would
has
that
to be careful, yeah.
possible? Would
Unit
that be
has to be careful.
possible? Yeah, possible. Perhaps you take like from different references, so they might use like different unit.
That's possible. Okay. Unit
Doctor,
is
actually for the equation for the K3 and K4, which is the last two question, the last two equation, the unit is mole per kg as Pascal squared.
mole per kg Pascal square. Yeah, berarti yeah. So where's my pen? So mole per kg Pascal square.
And second.
The second. So this unit, right? So you have this mole, and then per kilogram of the catalyst, and then this is then for sure this guy is then the in partial pressure. So this unit is correct. I mean, this is then the PSI unit for two order reactions. But if you have like two reactants like this, so it's one. So you have a Pascal square. So that's fine.
Sorry, but just now you said the PA squared refer to the order of the reaction. Is it?
Yeah, I mean, this is the order of the reactions, but then the unit of C, this is the Pascal. This is partial pressure. So if you have like if you plug in this unit, so mole per kilogram Pascal square, right? And then multiply with Pascal to the power of 1. Multiply with Pascal to the power of 1, right? What is that guy? That's this guy. And then you have this one is then 2. So this 2. So it's gone.
So,
So we have mole per kilogram.
based on the four equation, there are three different units of Pascal. For example, the first one, the first two equation is PA.
PA, like this. So the unit is then mole per kilogram PA.
Yeah.
Okay.
And
so
the third one is the PA squared.
Fourth one.
And the last one is Pascal 0.5.
Square. So in this case, so we know that this reaction is then the R then the minus K C, yeah. This is this guy, and then this is then the R equals to minus K C and then C, or minus K C square. That's this, and this one is then for sure K minus divided by this is then the C, the half, or minus K square C. This is this guy. So in this case, the exponential vector should be half, and then there is nothing else. If we have like a two components, our reaction number 4 is reaction number 4. So reaction number 4. So only one component is there, and then it's half. I don't know which one. I don't know which one. It has to be like either CO or H2, and then they are half. So if we okay, so now let's see this one. So let's use the obvious one. So you want to say So you want to CO2, right? So in this case, so yeah, for example, kinetic. So because if it's that means we have to sacrifice one. So CO2. I don't know which one. It's something that you have to look into the literature again. So I don't know which one, but then the one has to be active to make it like this, and the other one has to be like 0, and then this one is also something like that. Yeah, I don't know which one. I assume this one. And then the number 3 is square. So if it's square, that means it has to be square. Yeah, number 3, you say square, right? So this guy has to be square, has to be exponential of 2. And then number 4, it's at half. So yeah, either one has to be half. So I assume half on this. So if that is done correct, if I run this and I still don't get anything. Why is that so? I'm not really sure. Not really sure. Let me see my old file. Yeah, let's see if I can open an old file. 1 minute, yeah. Show you. See. I don't know if this is using kinetics. It's on something that we have to look into. This is also like methanol dehydration. Why is this? Because I put it already like where is that stuff? So input power law. 20 meter. 20 meters already. 200 meters. It's strange. Using this because I mean doing this calculation in Excel is straightforward. If you try to, because I don't see any if there is anything wrong with Aspen Plus, but we need to make sure that which number is suspicious between this and that. This is version number 1, very huge, 5 kilojoule. This one is also huge, kilojoule. This one is also, well, this one is not that big. This is all huge. You know what I mean? Yeah? If you look at DE, E is then the activation energy, right? So if we don't have enough energy to overcome this number, or if this number, or the other way around, this number is very big, the reaction is also not going further. So if I remove 1, 0, for example, see what happens. Also not something. Nah, see, something happens. Where is that? So this is kilojoule per mole. So 1500, and then you will then get CO and water. See, CO and water. See this number? So it's there. So then if we then if this number is reduced a little bit, and then you will get something like a lot more. See? Can you see?
Yes.
Yeah. So please be careful on the units of this guy, because means if you have like thousands or tens of thousands of this number, and then it's kilojoule per mole, it's not like kilojoule per kilomole. So it's something big. So it's a activation energy, something like right, something like this, right? So this energy. So this guy, if it's huge, then means if the energy that we supply, if the energy that we supply is not enough, okay, that's the strain boundary. So we only supply 240 degrees C. Yeah, only supply 240 degrees C, and then this amount of energy may or may not be enough to climb this mountain. But then if we have a different number, I mean, if you have different units, for example, I don't know if you have a number, it may be like this, something like this, and then this may be enough. I mean, your 240 degrees C may be something like this, 240 degrees C, yeah, about. And then if this is then the EA that you specify, and these reactions can happen. But then if this is then the EA that we specify, and then at 240 degrees C, we will not be able to climb this mountain. You follow? So for example, yeah, to say for example my main flow sheet. So now we go back to 152 900 something, right? This one. So if we run this, there's nothing happens. There's nothing happens. See, there's nothing happens, right? So it's not being consumed, so nothing happens. But then if you say for example, I put a lot more energy here, 600 degrees C. Also nothing happens, so it's too big. I know if you are not going to make it like as irrational as possible, but so just to give you an idea on the effect of the reaction kinetics. So nothing happens, but then if you go like reduce this by 10, can we see something? No. If we reduce it by 100, can we see something? See, we saw already something here. And then if we use like the one that we just did, so there are like a subtle difference already. Yeah, okay, I know. It's just very strange, guys. Now you are playing with very strange situation. And you can see, so you can see it consumes for these reactions to happen. Why is that stuff? See, we are losing in hydrogen already. So for this reaction to happen, you will need a lot more energy, and then this is already like on 200 degrees C gone. So it's even, I mean, it's a warning, so it's not really complete, I mean, converge, but it gives you like it tells you that something is wrong, which we know already. If we do this and we run it, so we still have some hydrogen left, CO2, but then we are making a water and then CO. So it's it's obvious from this exercise that we just did. Maybe this is then not so much of a, I mean, it will have an effect, yeah. See, less water, yeah, less CO. But if you prolong the reactor, meter, you will get more meter. Right? You prolong the reactor, means you prolong the reactions, you will get more. You will get more product, as in this case. It's gone, as in this case. Right? So if you are here and then you are there, it gives you different outlet concentrations or product concentration, right? So assume that your product concentration was something like that. So this is your product, So it's yeah. So my suggestion is that because if you want to do like techno-economic analysis, so we start with with like a commercial scale, and then from there on, you will then try to like size the requirement. For example, in the lab, you must have like that reaction must fulfill the certain pressure, temperature, and also because you have a fixed bed catalyst, you must have something like a space velocity or residence time. So it's up to you which one which term that you use. So this residence time, if you have like a flow rate, for example, we have like a 10 kTA, for example, so this one, you put like how much was that in like say 1 ton per hour, for example, right? So this 1 ton per hour, and then you can then say, okay, so this 1 ton per hour, and then you can then use the mass of the catalyst. So it's maybe I don't know, 1 meter cubic per hour. Yeah, this is just something that you don't know. But if start from here, and then use this. Scale it down to ton per hour, right? Convert it and then convert it to meter cubic per hour for the volume basis. And then, you know this, from the mass and then the density of the catalyst. And then using this guy, residence time, and then you can then calculate the length of the reactor. And then the volume basically of the reactor. So sorry, the volume of the reactions. No, confused now. So the volume of the reactions, we know the flow rates, and then the volume of the reaction. So the sorry, no, I'm now confused. So we have the residence time, we have the catalyst, we have the mass flow rate of the feed, and then volumetric flow rate of the feed, and then we can then say, okay, so now if it's 1 meter cubic per hour, so I have to fulfill this this hour residence time, right? This hour residence time. So and then multiply, or the multiply, right, with the residence times, which is an hour, and you can get your volume of the reactor. Right? So this volume of the reactor, and then you can then use a certain L over D, and then you can calculate the L, and then you can calculate the D, and then put this into the simulation. So then you know the D and then the length, the one that you put over here. So these numbers, instead of inch, it will be in meters, and then it will then feel like it has some basis, so it has it's practical in its essence. So it will have that feeling. So this number is correct instead of like this inch and inch. Yeah, I would suggest that you start with this with this approach, and then use that number in here, so we know for sure the setup is okay. Yeah, it's okay. Maybe it's not like an optimum, or we need to improve it further. That's the second step. So it's okay, and then the reaction rate is also okay. Where is that stuff? This one. So make sure that these units are all correct. Yeah, because this defines how much is then which reaction is then going. Right? You can tell that. From the numbers, I can tell which reactions will occur. Right? I've explained it to you. And then that's the kind of sense that I think you can also develop when you see these numbers. Yeah, please make sure that the units
are quite clear. Yeah, I now need to check back, especially the unit and also like the how do you get like the paper that you refer? I'm worried that you are using like different papers,
Yeah,
right?
yeah,
So it might be
yeah.
different.
yeah. Okay. So any other questions? So we haven't touched the we are still now struggling here, but but that's how Aspen works in a nutshell. I know that we are now, yeah, I don't know. Do you have any more questions that we can just shoot? Yeah. Yeah,
Doctor,
regard.
how about if we're dealing with reversible reaction?
It's fine. That means if you reversible reactions, that means you have to do something here. What is that stuff? Either you can if it's something like if the reactions look something like R so K and then C reactant and then times C product. Yeah, so you have like a reactant product. So this one can happen. This is where you put here the exponents of the product. So that's one. Or you could also say that equilibrium reactions, which we typically will have. I cannot do so. No. So say for example, and this one is, you know, say for example, I know water gas shift reaction, water, and then gas minus one. This is also equilibrium. Oh, yes. Water gas shift makes hydrogen and then CO2. Right, so CO is one. Water one. So equilibrium. No, really sure this is feeding to. Okay. Available products may be entered only when the reaction type is kinetic. Okay, no. This is okay. So use kinetic, that means you can then use exponents. If it's equilibrium, means we don't have to specify this guy. So click OK. And then the equilibrium is then your equilibrium, then obviously this paper. And then you can compute K equilibrium from the Gibbs energy, right? And then this is temperature approach and whatnot, and then you can then build it. So for example, so we use this typically this 1 minute, yeah. This is 800 dBc, 2 bar, 100. Water gas is more fraction. Okay, and then it goes to the yeah. So adiabatic, I don't know. R2, right? And if I run this, okay, what happens? Oh, action number one in R2 has solid component. Question number 1 and R2. Very strange. A minute. If there's no very strange. This is solid component. Solid substrate. Solid component. Where is that stuff? Hydrogen mix, hydrogen CO2 mix. Oh, this one is something I have to dig deeper. Yeah, why is it so?
I think we can do like the next session. Of course, once Aina need, then we are going to look into detail, especially on the reactor part. Is it okay, Doctor?
Fine. Yeah, this one also is
Need to,
interesting.
but I think we also need to go through on the reactor, like the kinetic data.
Yeah,
also.
that one for sure.
Yeah, then I think we can discuss better and look what are the things that Aina need to have and so on. So I think it's better to go through first back to the literature review.
Just see that reactions. You saw it already, right? I mean, it's
yeah. Now I realize which part is ne. So we need to go through back to the literature and see, and of course on the diameter and also the length of the reactor, because currently we are looking into the pilot scale instead of like other literature perhaps. Yeah.
Fine, but please approximate that using this thing.
Yes. Yeah. Okay.
But
it's already 12. I don't want to like
it's 12.
Yeah. I don't want to disturb your public holiday. I think for today it's quite clear actually. Even like doing the compressor, I did not realize that we need to do like multi stages, because normally we see in the literature is only. So I think it's just like, I think the next session will be more on like the reactor and perhaps the distillation column, more on that will be better. So that the student know how to start, and also the is it okay?
Yeah,
everyone?
I'm okay.
Yeah. How about others? Do you have any question?
Yeah,
No.
question that I can answer quickly. Yeah.
No.
Okay. So I think we know what to discuss next session. So I will plan with Dr. Zulfan. So perhaps that we are going to look in detail on the reactor and also on the distillation column. Is it okay, Aina? Sabirin. Siapa lagi kat situ? Kejap. Let me see. Atika. Ivy. Hakimi. Nisa. Afrina. Haiza. Do you have any question to ask before we end the session?
No, Doctor.
For me, no, Doctor.
Okay.
No, for now, Doctor.
No, okay. So I think we can stop now. And then perhaps we'll continue lah next session, hopefully in December. I think I prefer a face-to-face session, so it will be easier to show the equation and so on, the literature. So hopefully we can arrange another face-to-face session, maybe perhaps in December. So
Yeah.
if no one have any questions, so I think we can end the session. Is it okay? Okay. So thank you very much, Dr. Zulfan. Thank you very
Thank
much,
you.
everyone.
Thank you. Yeah.
Okay.
Thank you very
Bye-bye.
much, Dr. Fas.
Take
Thank
care.
you, doctor.
Bye.
Yeah. Bye bye.
Thank you, doctor.
Thank you.